This is the biggest warship the world has ever scrapped. 1,100 feet of steel, 90,000 tons, and buried deep inside the hull, where no torch can just cut its way in, sit 8 nuclear reactors. Not 2, 8. This was the first nuclear aircraft carrier ever built, and taking it apart is turning out to be harder than building it. The Navy now says the job will swallow more than $1 billion and stretch past 15 years. 15 years to take one ship apart. Here's the thing nobody tells you. Before a single saw touches that hull, the most dangerous part has to come out first, and it has to come out in one piece. Watch to the end, because the way they handle those reactors is the part the press releases skip right over. Let's back up and look at what they're actually dealing with. The USS Enterprise. The crew called her the Big E. She slid into the water back in 1961, the first carrier on Earth to run on atoms instead of oil. And for over 50 years, she sailed every ocean we've got. Then, in 2012, the Navy pulled her out of service for good. And that's where the real problem started. Because you don't park a nuclear ship in a field and walk away. Every system on board has to be drained, stripped, and made safe. First come the weapons and the classified gear, ripped out and hauled off under guard. Then the fuel oil, the hydraulic fluid, the lubricants, thousands of tons of liquid that can't just be dumped. Asbestos gets pulled from the walls, PCBs, lead, every toxic thing built into a Cold War warship. All of it tagged and bagged. And only after the ship is gutted and clean can anyone start thinking about the reactors. That alone takes years before the hard part even begins. Think about the scale of it for a second. This ship was a floating city. She had her own power plant, her own hospital, her own water-making machines, miles of cable running through her like veins. 4.5 acres of flight deck up top, 2,000 compartments below. Stripping a building that size would be a job on its own, and this building floats, and parts of it are radioactive, and every bolt of it was designed by the military to survive a torpedo. Nothing about pulling her apart is easy. Nothing about her was meant to come apart at all. So why is this one ship such a nightmare? 2 words: 8 reactors. A modern Nimitz-class carrier runs on 2. The Enterprise was the prototype, the first of her kind, and the engineers of the late 50s weren't sure 2 would be enough to push a ship this size. So they packed in 8 smaller reactors instead, each one feeding the turbines, all of them crammed into the belly of the hull. That made her fast, and it made her legendary. It also made her a problem nobody had ever faced, because now every one of those 8 has to be defueled, shut down cold, and dismantled. The good news, and it's real, is that the defueling is already done. The actual nuclear fuel, the spent uranium that powered her for decades, has been removed and shipped off to secure storage. But the reactors themselves, the steel vessels and the piping around them, those are still radioactive. And that is the wall every plan runs into. You can't just send a torch in there. Metal that's been sitting next to a reactor core for 50 years soaks up radiation. The steel itself becomes hot, not warm to the touch, but hot in the way a Geiger counter screams. Cut into it blind, and you spread that contamination into the air, into the water, onto the men doing the cutting. So before anyone goes near it, engineers map every inch of that compartment, measure the radiation point by point, and figure out exactly where the clean steel ends and the dangerous steel begins. It's slow, careful, expensive work, and there's no shortcut around it. Here's where it gets strange, and here's the part the headlines breeze past. The reactors don't get cut up on site like the rest of the ship. They get removed whole. Each reactor compartment, a massive sealed chunk of the hull, the steel vessel and all its contaminated plumbing, gets cut out as one giant block, capped, sealed shut, and lifted out in a single piece. We're talking pieces that weigh hundreds of tons each, hoisted by some of the largest cranes on the planet. They go on a barge. For the Navy's submarines, those reactor compartments travel by water all the way to a desert site in Washington state, a guarded trench called Trench 94, where they're buried in the ground to sit for thousands of years. The Enterprise is bigger, more complex, and the Navy is still deciding whether to send her to a government yard or hand her to a commercial shipyard. But the principle is the same. The hot part comes out first, sealed, and goes somewhere it can be watched for a very, very long time. Only then does the real scrapping begin. Now the ship is finally just a ship. A hollow shell of steel, no fuel, no reactors, no poison left inside. And this is where it turns into the biggest recycling job you'll ever see. They float her into a dry dock, pump the water out, and the carrier sits there, exposed, keel to flight deck, like a beached whale made of metal. Then the torches come out. Workers in cutting gear swarm the hull, slicing it apart section by section, plate by plate, the way you'd take apart an engine, but on a scale that's hard to even picture. The flight deck comes off, the hangar bays come down. The island, that tower where the captain stood, gets carved away. Every piece gets sorted, and the numbers are staggering. A carrier this size holds somewhere between 60 and 90,000 tons of steel and metal, and almost all of it can be recycled. That steel goes back to the mills, gets melted down, and comes out again as rebar, as beams, as the bones of new buildings and new cars. A warship that once carried 5,000 sailors ends its life as the frame of a parking garage you'll drive through without ever knowing. And it isn't just steel. There's copper in the wiring, thousands of tons of it, worth a fortune on its own. There's bronze, aluminum, brass fittings, and deep in her belly, 4 bronze propellers, each one the size of a house, each one worth millions just in raw metal. By the time they're finished, almost nothing is left to throw away. A ship that cost billions to build gets weighed, sorted, and sold off by the ton. And here's the math that should stop you cold. A brand new carrier today, a Ford class, costs around $13 billion to build. $13 billion. To take an older one apart safely costs over $1 billion more and eats 15 years. So every nuclear carrier represents a bill at both ends. One to build her, another huge one just to make her disappear. That's the hidden price of a nuclear navy that almost nobody talks about. The Big E was the first to face it, the prototype for a problem the whole fleet will inherit, because every Nimitz built after her is going to need this exact same treatment, one by one, for decades to come. So the next time you see a carrier on the news, remember, that ship has 2 lifetimes. The one where she rules the ocean, and the long, quiet, expensive one where the world has to figure out how to take her back apart without poisoning anything. And if you want to see how the most dangerous machines we've ever built get torn down and turned back into raw metal, you're in the right place. The next one is already in the dry dock.
Your smartphone weighs 5 pounds and holds a charge for 30 minutes. Your laptop's chained to the wall because the battery dies in 20 minutes. Electric cars don't exist. The battery would weigh more than the entire car and only go 50 miles. Cordless power tools, wireless headphones, anything portable, just impossible. All because we never figured out how to mine and refine one soft, silvery metal that stores more energy per pound than any other practical battery chemistry. Without this metal, we'd still be stuck with 70s technology. Nickel-cadmium batteries that weigh 10 times more, last 10 times less, and leak toxic heavy metals. Your phone would need a brick-sized battery. Today, we're going inside a facility in Nevada, where this metal is extracted from ancient underground brine. And I'll show you what properties make it irreplaceable and what the world looks like if we have to use something else. The Albemarle lithium facility at Silver Peak, Nevada sits in a desert valley 190 miles northwest of Las Vegas and has been producing lithium continuously since 1966. 10,000 feet beneath the surface lies a massive geothermal brine reservoir containing dissolved lithium chloride that's been concentrating for millions of years. The facility pumps this brine and processes 6,000 tons of lithium carbonate annually. If lithium had never been discovered, all batteries would use nickel-cadmium or lead-acid chemistry. A lithium-ion battery stores 160 watt-hours per kilogram. Nickel-cadmium stores 40. Lead-acid just 30. To match a modern iPhone battery, you'd need 2.5 pounds of nickel-cadmium instead of 2 ounces. The phone becomes a brick. Mobile computing doesn't exist. The first stage pumps geothermal brine from wells drilled 10,000 feet deep. This brine comes up at 200 degrees Fahrenheit, carrying 300 parts per million of dissolved lithium, along with sodium, potassium, and magnesium. The brine flows into massive evaporation ponds, covering thousands of acres, where the Nevada sun and desert wind do the work. Over 12 to 18 months, the water evaporates, and lithium concentration increases from 300 to 6,000 parts per million. This creates lithium's first critical property. Extreme reactivity makes it the lightest metal that can store electrical charge. Lithium atoms give up electrons more easily than any other practical metal, exactly what you need in a battery anode. Without this, you'd need heavier metals like nickel or cadmium, which means heavier batteries for the same energy. After evaporation, the concentrated brine moves to a chemical plant where it's treated with sodium carbonate to precipitate lithium carbonate as a white powder. This powder is washed, filtered, and dried to 99.5% purity. Lithium carbonate looks like fine white sand, ready to ship to battery manufacturers. Lithium's voltage characteristics become critical here. A lithium-ion cell operates at 3.7 volts. Nickel-cadmium runs at 1.2 volts. To match lithium's voltage, you'd need 3 times as many nickel-cadmium cells wired in series, tripling the weight and complexity. A 6-cell lithium laptop battery would require 18 nickel-cadmium cells. A 1-pound battery pack would weigh 7 pounds, making laptops impossible to carry. Lithium carbonate gets shipped to battery manufacturers, where it's processed into lithium metal or lithium compounds for battery cathodes and anodes. Modern lithium-ion batteries use lithium cobalt oxide or lithium iron phosphate for the cathode and graphite with embedded lithium for the anode. During charging, lithium ions move from the cathode to the anode through the electrolyte. During discharge, they move back, generating current. This reversible movement creates unmatched energy density. A lithium-ion battery handles 1,000 cycles while retaining 80% capacity. Nickel-cadmium manages 500 cycles. Lead-acid gets 300. Without lithium, devices need battery replacement twice as often, generating toxic waste because nickel-cadmium contains poisonous cadmium and lead-acid contains brain-damaging lead. Battery manufacturers shape lithium electrodes into thin sheets and stack them with separators, creating battery cells. Multiple cells connect to form packs for phones, laptops, cars, and tools. Each application demands specific energy density and safety features, but all depend on lithium's unique properties. Lithium's power-to-weight ratio is revolutionary. The Tesla Model 3 has a battery pack weighing 1,000 pounds that stores 75 kilowatt-hours, delivering 300 miles of range. With nickel-cadmium, you'd need 6,000 pounds of batteries to match that energy, but the car weighs only 3,500 pounds total. The battery weighs more than the car. You can't build a practical electric vehicle. Tesla doesn't exist. Electric cars remain a failed experiment from the early 1900s. Every batch of lithium and every battery goes through rigorous safety testing, and there's a specific reason why lithium battery safety standards are so incredibly strict. In 2016, Samsung released the Galaxy Note 7 smartphone with a lithium-ion battery that had a design flaw. The internal structure allowed the positive and negative electrodes to touch under certain conditions, creating a short circuit. Samsung had to recall 2.5 million phones globally. The recall cost them $5.3 billion. Airlines banned the Note 7 on flights. The incident nearly destroyed Samsung's phone business and proved that lithium batteries demand perfect manufacturing with zero tolerance for defects. Today, every lithium battery undergoes crush testing, puncture testing, thermal cycling between -40 and 150 degrees Fahrenheit, overcharging, and internal short-circuit simulation. The rejection rate for lithium battery cells is around 8%. Lithium that's passed all testing gets shipped to electronics manufacturers around the world. The Silver Peak facility produces 6,000 tons annually, but global production is roughly 400,000 tons because demand is massive. Without lithium, portable electronics barely exist. Your phone stays plugged into the wall, like it's the 80s. Laptops are 20-pound luggables with 30-minute battery life. Wireless earbuds, cordless drills, e-bikes, drones, portable medical devices, none of it exists. Anything portable and electronic requires a gas generator or an extension cord. Electric vehicles are impossible. Every automaker tried EVs with lead-acid or nickel metal hydride batteries in the 90s and 2000s. All failed. Maximum range 60 to 80 miles. Batteries died after 2 years. Without lithium-ion, Tesla never gets started. EVs remain a failed technology, and we're stuck with gas cars with no viable alternative. Renewable energy storage doesn't work at practical scale. Solar and wind need massive batteries to store energy when the sun doesn't shine or the wind doesn't blow. Without lithium, these systems would be warehouses full of lead-acid batteries weighing 50 times more, costing 10 times more, needing replacement every 3 years. Grid-scale energy storage is economically impossible. Renewable energy remains tiny because it's too unreliable without storage. Without this lightweight, high-voltage metal, we're stuck in a world where electronics stay plugged into outlets, portable devices don't exist, electric cars are impossible, and renewable energy can't replace fossil fuels. You've seen how brine containing 300 parts per million lithium concentrates through evaporation to 6,000 parts per million. How chemical processing creates 99.5% pure lithium carbonate. How lithium's properties create batteries with 4 times the energy density of alternatives. And why the Galaxy Note 7 proved that lithium production demands absolute precision. If this hooked you, subscribe for more content making modern life possible. Thanks for watching. Houston, Texas, high noon. The sun here doesn't just shine. It presses down on your shoulders like a heavy, hot blanket. The air above the scorching asphalt shimmers with heat waves, and your lungs fill with a thick, distinct smell. A mix of heated rubber, dry prairie, and diesel fuel. I'm standing at the gates of the Jinan plant, the world's largest tire recycling facility, and I can feel the soles of my boots starting to soften on the blistering Texas ground. Today, I'm not just a tourist. I'm a witness to a massive technological alchemical process, where what the world considers waste that won't decompose gets transformed into energy, and the very foundation of the highways we drive on. Houston didn't just greet me with sunshine, it slammed me with a wall of sticky heat that folks down here in Texas call the devil's breath. But the second I stepped through the entrance to Jinan's facility, the sounds of the city, distant highway hum and rustling wind, instantly shifted into something far harsher. Industrial chaos. But chaos that's perfectly ordered, rhythmic, almost primal. The first thing that hits you isn't the sound, it's the vibration. You don't just hear it. It rattles your chest like a low bass line at a rock concert. That's the giant motors firing up the heart of the plant. And spread out before me are the real black Himalayas. Thousands, maybe tens of thousands of used tires stacked into neat but staggering mountains. Everything's here. Thin wheels from compacts that only ever touched smooth asphalt, all the way up to massive donuts from mining dump trucks, treads tall as a person. They all came here to die, so they could be born again. The smell here is something else. It's not just the stench of rubber. It's a complex cocktail of heated polymer, traces of road tar baked into the treads, and hot metal. The Texas sun mercilessly scorches these black surfaces, and the heat radiating off them makes you feel like you're standing next to an open oven. The air between the mountains has solidified. It's thick and oily. I watch as another truck rolls up. The hydraulics groan as the bed lifts, and hundreds of tires tumble down with a muffled rumble. Thump, 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 cascading to the foot of the black mountain. This sound of rubber hitting rubber layers over that same endless vibration from the plant's engines. It creates this uncanny sensation of being inside a living organism. The plant breathes with this rhythm. It's hungry, and these mountains are its food. The vibration intensifies when the feed conveyors kick on. You see these massive manipulators, like the claws of prehistoric monsters, tearing into the piles, snatching their prey. In this place, on the edge between old junk and raw material, you feel tiny. We're following the conveyor belt that leads straight into the heart of the main floor. Here, that vibration I mentioned earlier transforms into physical force, pounding against your eardrums. We approach it, the primary shredder. If those mountains of tires were a graveyard, then this machine is the industrial meat grinder that knows no mercy. The first thing that hits you is the contrast between speed and power. You'd expect the shredder to spin at breakneck speed, flinging chunks of rubber in every direction like a blender. But no, the shredder's shafts move slowly, almost lazily. But within that slowness lies colossal torque, force capable of crushing stone. It's a deliberately engineered method. Low rotational speed prevents the rubber from overheating, keeping it from melting and sticking to the blades, which would turn the machine into a gummy trap. When the next tire, say, a massive wheel from a Texas pickup, hits the rollers, something happens that makes you flinch. The tire tries to hold its shape. Its steel belt, that same skeleton that carried tons of weight on the road, puts up one last fight. But hardened blades made from special alloy dig into the tread like the teeth of a prehistoric predator. 1 second, and you hear that distinctive crunch as the steel wires inside the rubber snap under hundreds of tons of pressure. In that moment, bright, angry showers of sparks fly out of the shredder's jaws. It's the friction of the steel belt against the blades, creating miniature lightning bolts inside the machine's dark belly. The heat here becomes almost unbearable. If it was just hot outside in Houston, near the shredder, the air heats up to a temperature where the sweat on your forehead instantly turns sticky with rubber dust. You can smell the frictional heat, sharp, metallic, with notes of burnt sulfur. It's the smell of matter being physically destroyed. Dust is everywhere here. It's not just floating in the air, it's dancing in the beams of industrial lights, settling on every surface like black velvet. These are tiny rubber particles released during the tearing process. You can see chunks falling from beneath the rollers onto the exit conveyor. This isn't a tire anymore. These are shapeless, torn scraps of rubber, roughly the size of an adult man's palm. Mangled strands of steel wire stick out from them, those same cord fangs that magnets will pull out in the next stage. The chunks of shredded rubber that just passed through the shredder's jaws move along on the conveyor belt. They look terrible, torn, dirty, hot, with those same mangled steel wire threads, cord fangs, sticking out from every black edge. Right now, one of the most cinematic stages at the Jinan plant begins. We're approaching the magnetic separation zone. Above the conveyor, where chunks of tires race by in an endless stream, massive blocks hang suspended. Overhead electromagnetic separators. They hang low, almost touching the black flow, humming with voltage. What happens on the belt resembles an uprising of the dead. When a ragged chunk of rubber enters the magnet's zone, the steel threads inside it react instantly. You see it with your own eyes. Metal wire that a second ago was part of a solid framework suddenly comes alive. With savage force, it tears free from its rubber prison, dragging the entire chunk with it, or simply slipping out like a knife through butter. Metal literally shoots upward, defying gravity. It looks like strange, aggressive magic. Thousands of steel needles and twisted wires slam into the magnetic belt with a loud crash, spinning perpendicular to the main conveyor. This is that endless clacking, the sound of thousands of metal fragments hammering into the separator's steel armor. The heat in this zone is unique. The magnets consume a massive amount of electricity and generate heat themselves, mixing with the warmth from freshly cut rubber. You're standing in a cloud of a specific smell, a blend of ozone, which always accompanies powerful electromagnets, and warm, raw metal. It's the smell of a forge, but without fire. Look to the left of the main conveyor. Another mountain is growing there. a mountain of pure steel. The magnetic belt carries the captured metal beyond the rubber stream, and, where the magnetic field vanishes, dumps it into a separate hopper. You're looking at springs coiled into spirals, long sharp needles, tiny metal chips. Everything gleams under the factory lights with a cold, bluish glow, contrasting sharply against the matte black of the rubber. Stripped of its steel skeleton, the rubber moves forward into the darkest and most airtight section of the plant. Now that the metal's gone, the rubber chunks look surprisingly light, but that's just an illusion before the final battle. We're entering the secondary granulation zone. High-speed granulators transform the torn pieces into perfect rubber crumb. The air here is thick with black snow, fine dust swirling through beams of light. Each granule passes through a system of vibrating screens, where they're sorted by size down to a fraction of an inch. But the real climax lies ahead, inside the sealed steel pyrolysis reactors. We approach the long, insulation-wrapped cylinders. This is the zone of quiet energy. There's no open flame here, but inside, hellish heat reigns, 850 degrees Fahrenheit. The key secret? Total absence of oxygen. The rubber doesn't burn, it distills. Can metal burn brighter than the sun? Sounds impossible. But one element does this every day, and we're about to touch its mystery right now. Imagine a material lighter than plastic, yet capable of withstanding loads that break steel. A material hidden in seawater, in stone, in the technology around us, but the way it's extracted looks more like alchemy than industry. And here's the thing. By the end of this video, you'll learn about a property of magnesium that even many engineers have never heard of. Ready to discover what giant furnaces, seawater, and 1,000-degree flames have been hiding? Magnesium is often called the metal that defies intuition. It's lighter than many types of plastic, weighing approximately 0.063 pounds per cubic inch, 1.5 times lighter than aluminum, and nearly 4 times lighter than steel. In your hands, it feels almost hollow inside, yet this metal demonstrates remarkable strength in alloys and can withstand loads its mass simply doesn't suggest. What's most striking is how it burns. Given sufficient temperature, magnesium produces light so intense that its brightness reaches close to 3,500 degrees Fahrenheit, and watching the flame without protection is impossible. That's precisely why magnesium flashes were once used in photography and pyrotechnics. During combustion, it forms white smoke of magnesium oxide, and the flame itself looks as if someone turned on a concentrated beam of sunlight. In nature, pure magnesium doesn't exist. It's bound up in minerals, and the two main sources are dolomite and seawater. Global estimates suggest that the oceans contain over 1.3 quadrillion tons of magnesium, making it one of the most abundant metals in a form accessible to humanity. However, extracting it from water is a complex and energy-intensive process. Picture an industrial facility on the coast where the sea is essentially raw material. Everything runs continuously through a system of powerful pumps. Pipelines stretch from the shore to the processing units, moving thousands of gallons per hour. The water flows into large open or enclosed basins resembling giant reservoirs, where it's filtered for the first time to remove debris, sand, and biological contaminants. After that, in similar tanks, a calcium hydroxide slurry is added. This happens through automated dispensers that feed the material into the water, so the reaction proceeds evenly. From the outside, it looks like a slow transformation of transparent seawater into a cloudy liquid, as if someone added fine white powder that gradually binds the dissolved magnesium into flakes of sediment. While the reaction continues, large mixers move through the pool, sometimes resembling windmill blades, only turned horizontally. They stir the liquid almost silently, so the sediment forms everywhere rather than clumping together in one spot. When the particles become heavier and start settling to the bottom, the liquid is pumped into the next settling tank. There it sits for several hours, and the solid fraction slowly settles, forming a dense layer that looks like wet cement. The upper part of the water is drained back into the sea or directed for retreatment, while the sediment is collected by special grabs or vacuum systems. Then the sediment is rinsed with fresh water and dried in powerful drying ovens that blow hot air at speeds capable of removing an entire layer of moisture in a minute. When the mass becomes brittle, it's moved to roasting furnaces. Inside, temperatures exceed 1,380 degrees Fahrenheit, and the material gradually transforms into magnesium oxide. From the outside, it looks like an endless white ribbon of powder, being fed by conveyor into the scorching chambers and emerging with a completely different structure. The final stage is electrolysis. The oxide enters sealed high-temperature chambers where it's mixed with salt flux. This happens either in smelting vats or in special crucibles, where the material gradually transforms into a thick, molten mass. The metal chamber walls glow red from the heat, and inside, the molten material looks like incredibly thick, scorching soup. At this point, electric current passes through it. You can only watch through protective windows, because everything inside appears to glow. Magnesium begins separating into tiny droplets that rise to the surface, since their density is lower than the molten mixture. It's collected using special ladles or drainage systems, and eventually the metal accumulates as shiny silver ingots, ready for further purification or casting into molds. In the case of dolomite, everything starts at the quarry, where the rock lies in massive layers. Extraction doesn't look like romantic stone chipping. It's the work of giant excavators, drilling machines, and blasting equipment. First, the rock gets crushed right on site. Massive jaw crushers chew through refrigerator-sized chunks and turn them into material that can move along conveyor belts. From there, the dolomite heads to factory hoppers, where machines precisely meter the flow and feed it into calcination kilns. The kilns work like giant tubes heated to 1,650 degrees. Inside, the dolomite slowly descends, while hot air, fed from below, passes through the entire layer of material. From the outside, you only see bright bands of glowing metal, but inside, something crucial happens. The dolomite breaks down into magnesium oxide and calcium oxide. After leaving the kiln, the hot mass travels along metal chutes and cools under powerful blasts of air. Next comes the stage where dolomite transforms into something resembling factory architecture. A tall tower with vessels, pipes, and tanks. Coke, or ferrosilicon, is fed into this tower, along with pre-crushed calcined dolomite. This mixing happens in specialized reactors that look like enormous drums, slowly rotating to ensure uniform contact between reagents. Everything appears as a continuous flow of dry, grayish powder sliding into the reduction furnace. Inside the furnace, the temperature climbs even higher, over 2,550 degrees. The heat inside is so intense that everything around glows with a dim red light. Under these conditions, magnesium oxide reacts with the reducing agent, and the metal transitions into vapor phase. This is one of the most distinctive features of magnesium production. The metal evaporates and rises through the furnace, while gaseous particles move into the condensation chamber. The chamber looks like a vertical steel cylinder, with cooled walls from the outside. Inside, magnesium vapors meet the cold surface, and the metal condenses as a shiny coating that resembles silvery frost. This coating gets periodically scraped off by mechanical scrapers or robotic manipulators operating in an environment with minimal oxygen access. The collected metal goes into protected containers, where it's melted again to remove residual impurities. The melting crucibles look like deep wells filled with glowing silvery molten metal, and extraction systems constantly work above them, protecting the metal from contact with air. The process ends with casting into molds, where magnesium cools and transforms into ingots. Each ingot represents the end of a long journey, from stone extracted by explosions to metal that emerged through evaporation and condensation. Global magnesium production holds steady at around 1 million tons per year. China supplies roughly 85% of that volume, while the United States, Israel, and Kazakhstan handle the rest. Interest in the metal grows annually because the aerospace, automotive, and electronics industries are hunting for the lightest materials possible. For example, using magnesium alloys in transportation cuts component weight by 20 to 35% compared to aluminum. That reduces fuel consumption and boosts overall efficiency. In electronics, magnesium shows up in laptop casings, camera bodies, and smartphones. It's not just light, it also absorbs vibrations well and dissipates heat effectively. In the United States, the share of magnesium in automotive parts has climbed from 3 pounds per vehicle 20 years ago to over 12 pounds in current models, and that figure keeps rising. Despite magnesium being lightweight, flammable, and extremely reactive, it's incredibly difficult to replace. It has a rare combination of mass, strength, and reactive properties that make it one of the most important structural metals of our time. And even though humanity has been producing it for only a century, the potential for its use hasn't come close to being exhausted. If current trends in aviation and electric vehicles continue, analysts predict global demand will reach 2 million tons within a decade. There's a metal out there almost nobody ever sees. But it's what turns steel into armor. How is it that just a few grams of vanadium per ton can boost a structure's strength by tens of % and literally lighten the weight of the world? Where does this element hide if it's almost never found pure in nature? And why is it often extracted not from ore, but from dark slag that others consider waste? Today, you'll witness vanadium's journey. Hellish furnaces, blinding molten metal, fire-colored powder, and the birth of ferrovanadium that transforms steel in an instant. And at the end, I'll reveal why control over vanadium is no longer just metallurgy, it's geopolitics. Vanadium holds a special place among industrial metals, though for most people it remains nearly invisible. It's rarely seen in pure form, it's not used for jewelry, and it's barely associated with everyday life. Yet vanadium became one of the key factors in the creation of armored steels and modern high-strength structures, without which bridges, skyscrapers, automobiles, and heavy machinery would be impossible to imagine. The history of vanadium as a metal begins in the 19th century, but it gained real industrial significance much later, when metallurgists understood how even tiny amounts of this element could radically transform steel's properties. In nature, vanadium almost never occurs in its free state. Most of the time, it's found in complex minerals and ores, particularly vanadium-bearing titanomagnetites, and also in magnetite, where it replaces some of the iron atoms in the crystal lattice. The major vanadium ore deposits are concentrated in China, South Africa, Russia, and a few other countries. Mining is typically done through open pit or underground methods, depending on how deep the ore bodies lie. Magnetite ore with vanadium impurities goes through crushing and enrichment after extraction, where they separate out a concentrate with high iron and vanadium content. At this stage, the material isn't split into individual metals yet. It's a complex mixture of oxides. Vanadium's next stop, where metallurgy becomes a true industrial spectacle. Melting magnetite concentrate happens in blast furnaces, or electric arc furnaces running at temperatures over 2700 degrees Fahrenheit. Inside the furnace, a mass of ore, coke, and fluxes slowly descends, passing through zones of different heat where solid chunks first sinter together, then transition into liquid. Molten iron collects at the bottom of the furnace, while lighter components, including vanadium oxides, concentrate in the upper slag layer. When the moment of release arrives, the furnace opens, and glowing streams pour out. Liquid slag glows with a blinding yellow-orange light, flows through channels, and throws up clouds of steam when it hits air or cooling surfaces. Right there in that seemingly spent mass lies the core treasure for vanadium production. After cooling, the slag transforms into solid, brittle chunks of dark material, deliberately collected and hauled away for further processing. Next up, crushing. Big pieces of slag pass through crushers and mills, getting ground into granular material or powder. The process hums with machinery, vibrations, and clouds of fine dust, immediately sucked away by filtration systems. The pulverized slag is prepped for chemical treatment, where vanadium needs to be extracted from an incredibly stable oxide matrix. Then the material enters reaction tanks filled with aqueous solutions of alkalis or salts. Under controlled temperature and constant stirring, leaching takes place. Vanadium compounds gradually transition into solution, shifting its color from pale yellow to rich orange or reddish. These visual changes directly indicate metal concentration and allow operators to monitor the process in real time. The resulting solution undergoes several purification stages. It's filtered, removing insoluble impurities, followed by precipitation, adding reagents that selectively bind vanadium. Inside the reaction vessels, a fine precipitate appears, gradually compacting and separating from the liquid. After washing and drying, this material becomes vanadium pentoxide, a bright powdery substance with a distinctive yellow-orange hue. From this moment on, vanadium stops being a hidden component in slag and becomes an independent industrial raw material. Vanadium pentoxide is then used to produce ferrovanadium, or is reduced to its metallic state. This entire sequence, from blinding molten metal to fine powder, vividly demonstrates how, deep within metallurgical processes, a material is born that defines the strength and reliability of modern steel. China produces 70,000 tons of vanadium annually, far exceeding the output of other countries and making it the global leader in both production and consumption of this metal. In terms of consumption, 90% of all vanadium goes into metallurgy, especially into high-strength microalloyed steels, where small additions of vanadium significantly increase mechanical strength, impact toughness, and fatigue resistance of structures. Ferrovanadium production is the critical link between chemical vanadium enrichment and the steel industry. It's in this alloy form that vanadium is most conveniently introduced into steel, precisely dosing its content and ensuring uniform distribution throughout the melt. The primary raw material for the process is vanadium pentoxide, obtained after processing slags or ores, along with metallic iron or iron-containing alloys. The process begins with charge preparation. Vanadium pentoxide is mixed with reducing agents, typically aluminum or silicon, and iron in strictly defined proportions. Next, the mixture is loaded into crucibles or electric furnaces, where conditions are created to reduce vanadium from its oxide state. Temperatures in the reaction zone reach over 3,600 degrees Fahrenheit, and it's at this moment that one of the most intense stages in the entire production line occurs. During aluminothermic or silicothermic reduction, the reaction proceeds extremely rapidly and releases a significant amount of heat. Vanadium oxides surrender their oxygen to the reducing agent, while pure vanadium transitions into a molten state and immediately dissolves in the iron. The result is liquid ferrovanadium with a specified metal content, typically ranging from 40 to 80% vanadium, depending on customer requirements. After the reaction completes, the melt is held to stabilize its composition, then poured into molds. As it cools, the ferrovanadium crystallizes, forming solid ingots or granules with a characteristic dark gray surface. The material is then crushed to a convenient size, packaged, and shipped to steel mills. The main value of ferrovanadium lies in its predictable behavior in molten steel. It dissolves quickly, is barely lost during melting, and allows precise control over microalloying. That's exactly why ferrovanadium became the standard form of vanadium supply for producing high-strength steels, from building structures to automotive components and armored products. The key feature of vanadium is that it works in microdoses. To get a noticeable effect, just tenths or even hundredths of a percent are enough. This means that for 1 ton of steel, only grams of vanadium are used, but those grams can boost yield strength, toughness, and durability by tens of percent. At the scale of millions of tons of steel, this delivers massive savings in metal, energy, and transportation costs. That's exactly why vanadium is often called the metal that lightens the weight of the world. Few people realize that vanadium also plays a role in long-term durability. Its compounds slow down grain growth at high temperatures and under repeated loading. This means structures made with vanadium steels age more slowly, handle cyclic loads better, and withstand sudden temperature swings. In real-world conditions, that translates to years of extra service life without repairs. Vanadium has become a critically important metal for infrastructure, and many countries have added it to their strategic materials lists. Control over vanadium flows means control over steel quality, and therefore over construction, transportation, and defense capabilities. This factor is increasingly shaping the geopolitics of metals. We're standing at a modern asphalt plant. It smells like hot tar, heated stone, and a little bit of my morning coffee, which I nearly spilled when I saw the scale of this metal structure. Most people think asphalt is just some black goop they smear on the road, but it's actually a whole science where every pound and every degree matters. We're about to break down this process into parts and see how a pile of rocks and a barrel of sticky liquid turns into a perfectly smooth highway. It all starts at the aggregate storage yard. These are massive mountains of crushed stone and sand you see behind me. This is serious business. The rocks are sorted by size. We've got really fine screenings, and we've got fractions half an inch or even 3/4 of an inch. Why does this matter, you ask? Because asphalt is like a cake. If you put in too many big nuts and not enough flour, it'll just fall apart under your car's wheels. A special loader grabs this crushed stone and dumps it into huge steel bins. Each container holds about 10 or 15 tons of material. Then begins a long journey on a conveyor belt. This rubber track stretches for dozens of feet and carries the stone to the heart of the plant, the dryer drum. Look at this giant metal tube slowly rotating. It's about 30 or 40 feet long. Inside it, a real flame roars. Why do we roast stone? Because there can't be a single drop of moisture in it. If water gets into the hot mix, it'll turn to steam and punch holes in your future asphalt, what we call voids. The temperature inside this drum climbs to 300 or even 350 degrees Fahrenheit. That's way hotter than your oven when you're baking pizza. Once the stone is properly roasted, it becomes super hot and bone dry. Now it needs to be lifted to the very top of the plant. They use an elevator for this, a vertical chain with buckets that stretches up 60 or 70 feet. Up there at the top, the scorching aggregate gets screened again through a set of sieves. It's like a final quality check to make sure no random wrong-sized rock messes up our road. Now we get to the star ingredient, bitumen. That's the same black sticky stuff that holds all the stone together. It's stored in massive vertical tanks that are constantly heated. If the bitumen cools down, it becomes hard as a rock, and we can't do anything with it. Each of these drums can hold up to 20 or 30,000 gallons of this black liquid. The bitumen is fed into the mixer under high pressure. It looks pretty epic, although peeking inside while it's running is a bad idea, unless you want to become part of the road. The actual mixing process happens in a giant mixer. They dump in a precisely measured amount of hot stone, add mineral powder, think of it like cement dust for thickness, and pour in the liquid bitumen. One mixing cycle takes about 40 or 50 seconds. In that short time, the mixer blades have to coat every single grain of sand with a thin layer of black gold. Imagine the responsibility. If you mix it poorly, the asphalt will start crumbling after the first winter. The finished asphalt comes out of the mixer at around 320 degrees Fahrenheit. It's basically molten black lava. From there, it either gets dumped straight into a dump truck bed, or it heads to a storage silo. These silos look like space rockets sitting on a launch pad. They can hold 200 to 300 tons of hot mix for several hours while maintaining temperature. This lets the plant run non-stop, even when trucks get stuck in traffic jams. I'm standing right now at the control panel. People sit here watching every pound of weight and every degree of heat on their monitors. A modern plant is a fully automated system. The operator just enters the recipe, and the computer decides how much sand, how much aggregate, and how much bitumen to mix. This eliminates human error, because a mistake of 0.1% in the formula can cost millions if the road has to be redone a year later. You've probably heard that asphalt is one of the most recyclable materials in the world, and it's true. This plant has a special unit for adding old asphalt that's been milled off other roads. They grind it up and put it back to work. It's awesome because we're not just tossing old rocks into a landfill, we're giving them a second life. The recycled material can make up 20 or even 30% of the new mix. That's good news for the environment and for the builder's wallet. Let's just take a quick detour right now and peek at how this goes down. Dawn breaks. The highway's blocked off with orange cones, and there's this thick steam rising from the hot asphalt. Feels like we're on the set of a volcano eruption movie. Our dump truck slowly backs up to the paver. This massive iron-tracked machine worth close to $500,000. The truck bed lifts, and 20 tons of black, steaming mass at 300 degrees Fahrenheit pours straight into the receiving hopper. Inside the paver, powerful augers are at work. Giant screws, just like the one in your meat grinder at home, only 12 feet long. They spread the hot mix evenly across the entire width of the lane. Behind the machine comes the screed plate, which doesn't just level the asphalt. It vibrates with crazy force to compact it initially. The machine leaves behind a perfectly smooth, black-as-night carpet, but it's still too soft. Step on it now, and your shoe stays there forever. And that's when the heavyweights enter the scene. The rollers. First comes the vibratory roller, weighing about 10 or 12 tons. Its steel drums rotate while simultaneously pounding the road at a rate of 40 or 50 strikes per second. You feel this vibration even through the soles of your sneakers from 30 feet away. This is necessary to squeeze out all the air and make the pavement solid. Behind it rolls a pneumatic tire roller on rubber wheels. It smooths the surface, sealing the tiniest pores so water can't get in. One pass after another, and we get a road that'll last 15 or 20 years. Let's go back to the plant. Another interesting point is air cleaning. You see that big box next to the drying drum? That's a baghouse filter. Inside it are hundreds of long fabric bags that capture dust. Only clean water vapor goes into the air, and all the dust is collected and goes back into the asphalt. So stories about these plants being super dirty, that's ancient history. Modern production is cleaner than the kitchen in most fast food restaurants. Now about volumes. A mid-sized plant like this can put out around 240 tons of asphalt per hour. Just to put this in perspective, that's roughly 12 big rigs worth of material. In a single 10-hour shift, this metal giant produces enough asphalt to lay several miles of new 2-lane highway. That's insane speed and massive responsibility. When a dump truck pulls up under the hopper, about 20 tons of smoking black mass pours onto it. Then the driver covers the bed with a special top so the asphalt doesn't cool down on its way to the paving site. If the temperature drops below 250 degrees Fahrenheit before it gets rolled out, you won't get a quality road. So logistics here is a real race against time. Watching one of these plants operate is like watching a really big, really complicated food processor. Nothing here is wasted. Every motor and every sensor performs its exact function. And while from the outside it looks like a pile of smoking, rumbling metal, it's actually a triumph of precision and engineering calculation. Every mile of highway we drive on vacation or to work started right here, in this hot, noisy place. Stick with me. We've got plenty more fascinating machinery and weird mechanisms coming up that make our lives more comfortable, even if we usually don't notice them. Today, I dragged you to a place so remote that cell service seems like technology from the distant future. And the main bosses here are massive excavators with wheels big enough to comfortably fit a small studio apartment. We're starting our journey at a nickel mine. Have you ever wondered where that perfect shine on a surgeon's scalpel comes from? Or why your pot doesn't turn into a pile of rust after cooking your first batch of borscht? The answer lies here, 1,600 feet beneath our feet. Nickel. This is the guy that makes steel tough and resistant to just about everything. But finding it? That's an adventure for the patient. Look at these numbers. To extract just 1 ton of pure nickel, miners have to move and haul to the surface about 100 tons of ore. That means the useful metal content in this rock ranges from 1 to 3%. Massive underground machines load up rock that looks like ordinary gray stone, but hidden inside is the promise of future strength. One of these dump trucks carries 240 tons of rock at a time. That's the weight of roughly 40 adult elephants, if you like those kinds of comparisons. After we've brought the ore to the surface, it's got a long journey ahead to the processing plant. There, the stone gets crushed into fine sand, washed, sifted, and turned into concentrate. It's not metal yet, but it's getting close. Then this concentrate gets shipped to a metallurgical plant. And this is where things get really interesting and really hot. We're standing inside a shop where electric arc furnaces are doing their thing. Here, temperatures climb to 3,000 degrees Fahrenheit. That's roughly 10 times hotter than your home oven when you're trying to roast that holiday duck. All this molten metal churns like fiery soup, glowing so bright that without special goggles, you really shouldn't look at it. Not if you plan on seeing anything else for the rest of your life. Into the furnace goes scrap iron, that same nickel, and one more critical player, chromium. Chromium is a whole story unto itself. For steel to officially earn the right to be called stainless, it needs at least 10.5% chromium. When this metal contacts oxygen, it forms an invisible, incredibly thin oxide film on the surface. It's so thin we can't even see it, but it becomes that impenetrable barrier that keeps the iron from oxidizing. So stainless steel doesn't rust, not because it's magical, but because it's already coated with a protective layer at the atomic level. Once the steel melts, it goes through a procedure called argon-oxygen decarburization. Sounds like the title of a PhD thesis, but the idea is pretty straightforward. Surgical steel has to be incredibly pure and contain extremely little carbon. Too much carbon? It'll buddy up with the chromium, steal it away, and the steel loses its resistance to corrosion. A mixture of gases is blown through the molten metal under immense pressure, literally burning out the excess carbon while leaving all the useful additives in place. The whole process takes about 90 minutes. You can't rush this. One mistake in the proportions, and instead of a valuable medical instrument, you get ordinary rebar that'll be covered in rust spots within a few months. Next, this fiery liquid gets poured into continuous casting machines. Steel solidifies into long, massive strips that professionals call slabs. A single slab can weigh 20 tons and stretch about 40 feet long. When they come out of the machine, they're still glowing dark red, radiating so much heat you could toast bread in a fraction of a second without even getting close. Then these slabs head to the rolling mill. Picture a giant version of a rolling pin, except instead of dough, you've got a 20-ton chunk of red-hot steel, and instead of a baker's hands, you've got massive rollers pressing down on the metal with thousands of tons of force. The metal gets run through these rollers again and again, getting thinner and longer each time. From a slab 8 inches thick, steel workers produce coils of steel ribbon just a few hundredths of an inch thick. The speed at which steel flies through these rollers in the final stages hits 40 feet per second. It looks like an actual fiery arrow racing through the plant. Now let's jump to a completely different place. Gone is the hellish heat and roar. We're at a medical instrument factory. The atmosphere here feels more like an operating room or lab, sterile, quiet, and fanatically detail-oriented. That steel ribbon we saw earlier, it's cut into small blanks. Then each blank is heated again, but now in small induction furnaces and forged in special dies. That's how the rough profile of a future clamp, forceps, or scalpel emerges. After forging, the real precision work begins. Craftsmen use grinding machines and hand finishing to perfect every curve. This is absolutely critical, because a surgical instrument must be perfectly smooth. Not a single burr or microscopic pit where bacteria could hide and multiply. The tolerances here are so tight they're measured in microns. A human hair is about 50 microns thick. We're talking about precision down to 5 or 10 microns. Once the instrument takes its final shape, it goes through heat treatment. It's heated to 2000 degrees, then rapidly cooled. This makes the steel hard, so the scalpel won't dull after the first cut, and the clamp won't bend in the doctor's hands. But after hardening, the metal becomes brittle, so it's heated again slightly, a process called tempering, to restore the necessary flexibility. One of my favorite stages is passivation. This is when the finished, already shiny instruments are immersed in baths of strong nitric acid solution. You'd think, why torture a finished product? But the acid does something really useful. It dissolves any microscopic particles of regular iron that might have gotten on the surface from the machines or the craftsman's tools. This cleaning allows that same protective chromium film we talked about at the beginning to become even thicker and stronger. After this treatment, the instrument can handle thousands of sterilization cycles in autoclaves at 273 degrees Fahrenheit under 2 atmospheres of pressure and stay shiny and clean for years. Let's crunch some numbers here, because they always help us grasp the scale of what's happening. The world produces about 50 million tons of stainless steel every year. If you stretch that metal into a thin wire, you could wrap our entire planet thousands of times. But only a tiny fraction of that steel, less than 1%, gets to become a surgical instrument. To manufacture one quality operating room set, you've got to process hundreds of tons of rock, burn through thousands of kilowatt hours of electricity, and run over 30 different quality tests. For instance, one ordinary surgical clamp passes through the hands of at least 12 different specialists, from the blacksmith to the quality controller, before it lands in its packaging. Quality control here is so strict that a tool gets scrapped even for a microscopic scratch on the surface, something the naked eye wouldn't even notice without serious magnification. And here we see the final result, a tool weighing less than 2 ounces, but packed with the labor of thousands of people, from those who descended into dark mines for nickel, to those who calibrated the lasers for marking finished products. It's a long journey, where every step is a battle for quality and purity. Subscribe to the channel so you don't miss our next deep dives, because the world of manufacturing is way more fascinating than it seems at first glance. Thanks for watching, take care of yourselves, and choose only reliable tools for your life. See you in the next video. By the way, what do you think? Will humanity ever find a metal even stronger than today's steel alloys? Or have we already hit the peak of what's possible in this field? Every year, the world mines over 900,000 tons of rare earth metals. Without them, not a single smartphone, electric car, or wind turbine would work. But there's one place where most of them are born. Baiyun Obo, a massive quarry in the heart of China that supplies 70% of all the rare metals on the planet. Here, the earth glitters with metallic dust, and every dump truck hauls raw material for the future. But behind this shine hides a dark truth. Lakes of toxic waste, and the price nature pays for technological progress. Stick around till the end, and you'll discover how dust and poison create the foundation of modern civilization. The story of Baiyun Obo started back in the 1920s, when geologists discovered a strange ore in this area, a mix of iron and minerals unknown at the time. In the 1950s, Chinese scientists realized that hidden here was a treasure trove of rare metals: neodymium, praseodymium, cerium, yttrium, and lanthanum. Since then, Baiyun Obo has become the heart of China's strategy that would eventually turn the country into the undisputed leader of the global rare earth market. Every year, about 270,000 tons of rare earth concentrate are mined here, more than all other countries combined. It all starts simply. Massive dump trucks the height of a 2-story building pull up to the edge of the quarry, where giant excavators with buckets like a dinosaur's mouth rip out chunks of monzonite ore. Each bucket can hold over 100 tons. The dust rises in columns, and it feels like the very air here is saturated with metal. But extracting the ore is just the beginning. The real value is hidden in microscopic inclusions of rare earth minerals. Their share in the rock is only a few %, so after extraction, the ore is crushed and sent to processing plants, where a complex chemical story begins. First, the ore is ground to dust, then subjected to flotation, a process where particles suspended in water are separated using reagents. Rare earth particles stick to air bubbles, rise to the top, while the rest settles to the bottom. This is just the first step, because the concentrate still contains plenty of impurities: iron, calcium, fluorine. Next comes chemical extraction, which transforms the concentrate into high-purity oxides. This is an extremely complex process. In specialized reactors, the ore is treated with acids, usually sulfuric or hydrochloric, sometimes with the addition of fluoride compounds. After this, the resulting solution is separated into fractions using organic solvents. Each element, neodymium, praseodymium, cerium, has its own chemical quirks, so the process requires dozens of sequential cycles of extraction, precipitation, filtration, and drying. It's these oxides that then go into the production of permanent magnets, the main consumer of rare earth metals. For example, one iPhone might contain less than 1/10,000th of an ounce of neodymium in the speakers and vibration motor. In a modern wind turbine, nearly 1,400 pounds of this element. And here's the wow fact. Just 1 gram of neodymium can provide a magnet for a turbine that generates electricity for roughly 1,000 homes. It sounds like an energy miracle, but it has a flip side. The problem is that chemical processing of rare earth ores is extremely toxic. Every gram of pure metal means tons of waste. In the Baotou area, near Bayonobo, real waste lakes have formed. Black, acidic bodies of water where radioactive elements, fluorides, and heavy metals accumulate. They're visible even from satellite. Even with modern cleaning technologies, chemical processes leave their mark on the environment. Local residents tell stories that, over the past decades, dust from the quarry and processing plants has changed the soil color, and grass around the area has been growing worse. However, the Chinese government is taking measures, implementing closed-loop water systems, controlling acidic runoff, and converting some facilities to new, green technologies, where instead of traditional acids, they use ionic solutions and membrane separation. All this is being done not just for environmental reasons, but also because China aims to maintain its dominance in the global rare earth metals market. Today, it accounts for 70% of global production and over 90% of finished oxide and magnet production. Other countries, the US, Australia, Vietnam, Malaysia, are trying to develop their own deposits, but they haven't come close to Chinese scales yet. Bayonobo has become more than just a quarry. It's a symbol of the technological era, where Earth transforms into smartphones and ore becomes electric wind. Right here, among mountains of metallic dust, the elements that power digital civilization are born. There's a certain irony in this. In the quest to create a green future, humanity has become dependent on one of the dirtiest industries. Magnets for electric cars and turbines, batteries, solar panels. All of this requires metals extracted from places like Bayonobo, and the greater the demand for clean energy grows, the deeper this giant wound in the earth becomes. Despite this, for China, Bayonobo is a source of national pride. Thousands of people work here, and the territory itself is equipped with modern infrastructure, conveyor systems, automated drilling rigs, chemical plants that operate almost without human involvement. On the surface, sensors are installed that track air composition, and in reservoirs, pollution levels are monitored in real time. Every dump truck descending into the quarry is part of a giant machine that supplies the world with energy, data, and sound. And when we hold a lightweight smartphone in our hands, it's worth remembering that a piece of this device, maybe even that very magnet in the speaker, was once dust in the Mongolian desert. Neodymium is one of the most famous, and at the same time, most mysterious rare earth metals. It's a silvery white, shiny, fairly soft metal that easily oxidizes in air, so it's usually stored under a layer of oil, or in an inert atmosphere. Sounds unremarkable, but this element has become the quiet engine of the modern technological revolution. Without neodymium, wind turbines, electric cars, headphones, laptops, and even rockets wouldn't work. In pure form, neodymium doesn't have the magnetic properties it's valued for. They appear when it's combined with iron and boron, forming an alloy. This is the material used to make the most powerful permanent magnets on Earth. One neodymium magnet can hold weight hundreds of times its own. In industry, it's called a supermagnet, and for good reason. It's what makes compact electric motors, miniature speakers, and highly efficient generators possible. One study indicates that between 2001 and 2021, Bayun Obo supplied about 60% of neodymium from China's total neodymium extraction. On one hand, Bayun Obo is a remote, harsh, and dusty place. On the other, it evokes an almost magnetic curiosity in those who want to see what modern civilization looks like in its raw material form. Bayun Obo today is not just a mine, but an entire complex with its own small town, a rare earth elements museum, and even a special viewing platform from which you can see the giant pit going hundreds of feet deep. The flow of tourists here is small by Chinese standards, but steady. These are mainly engineers, geology students, bloggers, eco-tourists, and those fascinated by industrial landscapes. In 2019, local authorities even declared Bayun Obo part of the Industrial Heritage of Inner Mongolia route to show how mining and processing have transformed the region. In tourist brochures, this place is called the heart of the rare earth planet. The road to the quarry leads through endless plains and low hills, where the wind almost never stops. The air carries the smell of metal, and from a distance, the quarry looks like a giant amphitheater, where Earth plays the starring role. Tourists aren't allowed close to the mining zone. It's too dangerous, but there are several safe spots from which you can take photos. The most striking moment is when quarry dump trucks slowly move at the bottom of the pit. They look like toys. The scale is so massive. Imagine a metal that looks like a liquid, moves on its own, and for centuries was thought to be the key to immortality. What if this very substance drove scientists insane, killed entire cities, and still hides underground today, waiting for human error? Every year, the world produces and isolates thousands of tons of this stuff. But the real danger isn't in the numbers. It's that mercury never disappears. It migrates, it accumulates, it comes back. From alchemists who breathed in its vapors to tragedies born from normal water and fish, this is the story of a metal humanity called poison way too late. Stick around till the end, and you'll learn why even today, mercury isn't seen as a resource. It's a threat you can't just bury. In ancient civilizations, people knew about mercury long before they understood how dangerous it was. They found it in nature as cinnabar, a bright red mineral that released mercury when heated. Chinese alchemists thought it was an ingredient for immortality. Egyptians used it in rituals. Romans put it in mirrors and cosmetics. Spoiler, none of this ended well. But back then, nobody was reading safety labels. In medieval times, mercury became the star of alchemy. It symbolized change and transformation because it could be both metal and liquid at the same time. Alchemists believed it was the key to making gold. They breathed its vapors, touched it with bare hands, mixed it with other substances, and genuinely wondered why their hands were shaking, their memory was failing, and weird psychological symptoms were kicking in. That's how the mad scientist trope was born. No memes required, just real consequences. The modern era brought mercury an even bigger upgrade. It was used in thermometers, barometers, manometers, fluorescent lamps, batteries, switches, and even medicine. Yep, doctors once prescribed mercury as medication, for infections, even for bad moods. The biggest fail? Treating syphilis with mercury ointments. The disease might not go away, but poisoning was guaranteed. Who remembers mercury thermometers? Drop a comment if you've got one. It was in the 20th century that humanity started to collectively realize mercury wasn't just weird, it was genuinely dangerous. It's toxic in any form, but especially sneaky because it evaporates easily and builds up in your body. Nervous system damage, coordination problems, memory loss, vision issues. This isn't some thriller script. It's what chronic mercury exposure actually does. The phrase "mad as a hatter" didn't come out of nowhere. Hat makers used mercury compounds, and craftsmen literally lost their minds. Then there's the dark chapter of ecology. Mercury doesn't disappear. It migrates. When it hits water, it transforms into methylmercury and enters the food chain. Fish eaten by humans, and suddenly the toxin's inside you. The tragedy of the Japanese city of Minamata became the symbol of this problem. Mass poisoning affecting thousands of people proved that a little mercury is a myth. In the mid-20th century, in the Japanese coastal city of Minamata, a chemical plant spent years dumping wastewater loaded with mercury compounds into the bay. The water looked normal. Fish were biting. Life went on, until people started getting mysteriously sick. First came the seizures, tremors, loss of coordination, speech problems. Then, paralysis, blindness, death. Mercury hit children especially hard. Infants were born with severe nervous system damage, even though their mothers often showed no obvious symptoms. The culprit was methylmercury, accumulating in fish and shellfish, the foundation of the local diet. The toxin didn't disappear or dilute. It intensified at every level of the food chain. For decades, the company and authorities denied responsibility, while victims fought not just disease, but indifference. Minamata showed the world a simple, brutal truth. Even minimal doses of mercury can have catastrophic consequences when they become part of the environment. It was the end of the illusion of safe mercury. Mercury deposits exist today, but attitudes toward them are radically different from centuries past. The primary natural source of mercury remains cinnabar, a bright red mineral, mercury sulfide, which forms in hydrothermal deposits, often near volcanic zones, and fractures in the Earth's crust. It's from cinnabar that metallic mercury was historically obtained through roasting, and this process has remained virtually unchanged technologically. What changed were the scale and the regulations. The largest known mercury deposits in the 20th century were developed in Spain, Italy, China, Kyrgyzstan, Mexico, and Algeria. Spain's Almaden deposit was once considered the world's largest, and for centuries supplied a significant portion of global production. Today, it's basically mothballed, like most classic mercury mines. The reason's simple: demand tanked, and the environmental and health risks became too obvious to ignore. China remains the main mercury producer now, but even there, extraction volumes are way lower than in the past. Many countries aren't opening new deposits. They're working with existing stockpiles or secondary mercury recovered from industrial waste recycling and dismantling old equipment. The world has essentially shifted from active mining to a mode of control and reduction. Modern mercury deposits are increasingly viewed not as a future resource, but as a problem that needs to be safely isolated. Some deposits get shut down, others are reclassified as geological landmarks or monitoring sites. Mercury still sits deep within the planet's core, but its story as a strategic metal is nearly over. Now it's an element humanity handles with extreme caution. Underground mercury ore extraction in China typically starts with a narrow portal carved into rock, the entrance to a mine shaft. It might look like a dark rectangle in stone, reinforced with concrete or metal frames. Inside, a tunnel several yards wide, where small mining vehicles can pass through or conveyor belts can run. The working space is cramped and low. The ceiling's propped up with beams, the walls damp, streaked with reddish or dark brown veins of cinnabar. Lighting: cold fluorescent lamps casting harsh shadows. The air's heavy, so ventilation is critical. Along the tunnels run air ducts, humming and pushing fresh air deep into the mine, while simultaneously pulling out dust and gases. The ore itself is extracted using drill and blast or mechanical methods. First, drilling rigs bore a series of holes into the rock. It looks like rhythmic metal biting into stone. Then, if blasting is used, minimal charges are placed in these holes. The explosions are controlled, small. The goal isn't to destroy everything, but to peel away the rock. After that, the tunnel fills with dust that settles for minutes, while ventilation runs at full blast. Next, mechanization takes over. Front-end loaders rake up the broken rock, or gather it in buckets and dump it into mine cars or onto a belt conveyor. The stone looks uneven, with flecks of red. That's cinnabar, the main target. People try not to touch the ore with bare hands unless they have to. The dust is dangerous, so workers wear respirators, thick coveralls, gloves. How strictly this is enforced depends heavily on the specific operation. If it's a semi-underground or open-pit mine, the picture is different. There you'll see step-like benches cut into the rock where equipment moves around. Excavators strip away layers of ore, trucks haul it up to the surface. But even here they try to avoid huge open spaces, mercury dust and fumes, enemy number one, which is why open pits are less desirable for this kind of metal. All that ore doesn't sit around in the mine for long. It's immediately transported to the surface in sealed containers or on covered conveyors to minimize dust dispersal. At the mine exit, you'll often see washing stations, equipment, and sometimes the workers themselves get hosed down so they don't carry cinnabar particles beyond the production zone. After extraction, the ore is crushed and sent for heat treatment. Cinnabar is heated in specialized furnaces, where the mercury sulfide breaks down and the metal evaporates. This stage is the most dangerous. Mercury vapors are toxic, so modern facilities are equipped with sealing, condensation, and filtration systems. The vapors are cooled, after which the mercury transitions to a liquid state and is collected in sealed containers. Formally, all these processes are supposed to occur in a closed loop with no emissions into the environment. In practice, this is where the biggest questions arise. At large state-run or licensed operations, oversight is stricter. There's air monitoring, waste disposal protocols, and tracking of every kilogram of metal. At smaller or semi-legal operations, the risks are significantly higher, and these have historically been the source of local contamination and poisoning. What if I told you that inside the most dangerous machines on the planet hides a steel secret that can only be created once, and a mistake costs an entire nation? That there's an ingot that cools underground for 6 weeks and withstands pressure that would shatter mountains? This giant is born in fire, exceeding 5,000 degrees Fahrenheit, endures months of forging, blows of tens of thousands of tons, and thermal shocks that would explode ordinary metal into fragments. Stick around till the end. You'll discover what these monoliths are actually built for, and why, without them, the modern world would simply grind to a halt. It all starts in the foundry. To create a monolithic ingot, you need liquid steel of impeccable quality, poured into a mold in one continuous stream. This is a stage that demands maximum coordination, because we're talking about thousands of degrees and hundreds of tons of metal. A striking example of such an engineering feat was a record-breaking pour carried out by the British firm Sheffield Forgemasters in 2015. The company's metallurgists successfully handled the pouring of 607 tons of liquid steel into a giant casting pit. To put that volume in perspective, it's nearly the weight of a full-sized Airbus A380 passenger jet. The pouring process is critically important. The steel must not only be melted, but also purified to a level that meets the strictest customer requirements, for example, for reactor components. This means minimizing impurities, gases, and slag. A continuous pour ensures that there won't be any layered defects or boundaries in the ingot structure that would reduce its mechanical strength. During casting, the steel must be fully degassed. Oxygen and nitrogen levels are controlled at levels often not exceeding 20 parts per million. Excess gases can cause microvoids to form inside the monolith during cooling. Immediately after pouring the molten metal, which can exceed 2700 degrees Fahrenheit, time becomes the most critical factor in this process. Unlike small ingots that can cool quickly, a steel giant weighing hundreds of tons cannot be cooled rapidly. If cooling happens too fast, it leads to massive internal stresses, cracks, and structural defects because the outer layer solidifies while the steel inside is still liquid. To ensure uniformity of the crystalline structure, The 607-ton ingot was left to cool in the casting pit for 6 weeks. This is a controlled, incredibly slow process, during which the steel gradually solidifies, dropping to a temperature of around 2000 degrees. This slow crystallization allows the metal to avoid unwanted phase transformations and guarantees a high-quality macrostructure, which is the key to the strength of the future component. Only after this lengthy solidification period is complete, the steel monolith, which after shrinkage and removal of the defective top portion weighs approximately 320 tons, is carefully extracted from the ground. The extracted ingot, despite its weight, is not yet a finished blank. It has a cast, coarse structure with large crystals. To transform it into strong, homogeneous metal capable of withstanding extreme loads, forging is required. Forging 500-ton ingots demands hydraulic presses with working forces ranging from 10,000 to 20,000 tons. For example, forging the largest reactor components requires presses with a capacity of 40,000 tons. Before forging, the ingot is again carefully heated in specialized furnaces. This process can take weeks to guarantee uniform heating throughout the entire volume of metal. The forging itself is done on giant hydraulic presses capable of creating pressure in the tens of thousands of tons. The press breaks down large, brittle cast crystals. The pressure compresses the metal, eliminating microscopic voids that may have formed during casting. The metal gains a directional fibrous structure, which significantly increases its strength, toughness, and fatigue resistance. The forging process for such an ingot takes several months. It's a constant cycle of heating, pressing, rotating, and reheating. Each press stroke is a precise calculation aimed at achieving the required internal geometry and mechanical properties. The energy needed to maintain the furnace for heat treating ingots during a 2-week cycle can exceed 100,000 kilowatt hours. That's comparable to the annual electricity consumption of dozens of typical households. During heat treatment, the allowable temperature deviation in the furnace throughout the entire volume can be only 40 degrees, which requires the use of high-precision multi-zone control systems. After shaping the ingot, we move to heat treatment. This is the final, critically important stage for tuning the internal structure of the steel. A multi-ton steel monolith that's just survived months of casting and forging is like a clumsy giant whose final character hasn't formed yet. It's strong, but its internal structure is still chaotic, riddled with invisible internal stresses. The first step is normalization, or, as we call it, homogenization. The idea is simple. We basically stir the metal structure so it becomes absolutely uniform throughout the entire volume. This ensures that at every point in the workpiece, both on the surface and deep inside, the steel has identical properties. It's like evening out the temperature in an oven so your cake bakes perfectly. Then comes the most dramatic moment, quenching. The workpiece is heated to a very high temperature, bringing it to peak plasticity. And then, rapidly, but under strict control, it's cooled. This could be a water or oil bath. This shock to nature transforms the soft steel structure into something maximally hard and strong. This gives the part its core fighting strength, but there's one side effect. The metal becomes brittle as glass, and massive internal stresses appear. If you leave it in this state, it can crack from the slightest impact. That's why the final, and most humane stage is tempering. The piece is carefully reheated, but this time to a much lower temperature. The goal isn't to change the strength, but to release the internal stresses that formed during rapid quenching. This process is like taking a deep breath after stress. It increases the steel's toughness, making it resistant to impacts and loads, eliminating brittleness. Only after successfully completing this full month-and-a-half cycle of character hardening is the steel ready to become part of a reactor or a giant press. But what are these steel giants for, into which so much time and resources have been invested? They become critically important components in industries where the price of failure is unacceptably high. For example, in nuclear power, these ingots are transformed into key components of high-pressure reactors. Picture this: pressure, temperature, and radiation demand absolute reliability. And there can't be any seams or welds that might give way. You need just one thing: a solid, continuous monolith capable of withstanding extreme loads for decades. In heavy machinery, these giants become frames for the world's largest presses. These presses shape automotive frames, aircraft parts, and ship components. A frame that won't deform under thousands of tons of load has to be cast in one piece. And of course, there's power generation. Rotors for the largest steam turbines, or crankshafts for massive marine engines that drive supertankers and container ships. In these components, you need guaranteed strength against bending and secondary loads, and only steel produced through this incredibly complex process can deliver that. Picture a liquid that goes through at least 10 different transformations before it ends up in the tank of a truck, tractor, or generator. It's boiled, compressed, broken down into molecules, reassembled, cleaned with hydrogen, and tested dozens of times. All of this so an engine can run for hours under load, in scorching heat and freezing cold, without failures or surprises. Diesel fuel seems ordinary, but it's actually one of the most complex products of modern industry, where behind every gallon stands engineering, temperature, and cold calculation. Diesel fuel doesn't just appear from crude oil, like gasoline from a pump. It's the product of a long, hot, and highly controlled chain of processes, where crude oil is gradually transformed from a dark, heavy liquid into a precisely defined mixture of molecules capable of running reliably in an engine. Everything starts with oil, but then it's literally broken down into components, sorted, cleaned, and reassembled, this time in the right form. Crude oil begins its journey far from the refinery, at oil fields, where it's lifted from the Earth's depths through wells. Along with the oil, water, gas, sand, and small rock particles come to the surface. So right at the extraction site, it's partially settled and the largest impurities are separated out. Once it's out of the ground, the oil hits the road. Most of the time, that means pipelines, continuously pumping millions of tons of liquid across hundreds, even thousands of miles. Where there are no pipes, tankers or rail cars take over. Either way, by the time the oil reaches the refinery, it's still far from ready. Before processing can begin, the crude has to be prepped. It almost always contains water, dissolved salts, and solid particles. Leave those in, and they'll wreck the equipment fast. Salts cause corrosion, water messes with stable heating, and solids wear down pumps and pipes. So the oil gets heated and run through desalting and dehydration units. There, it's mixed with fresh water to wash out the salts, then an electric field forces the water to separate and settle. After that, the crude is much cleaner, and a lot safer for what comes next. The prepared crude oil enters the refinery's main unit, the atmospheric distillation column. This is a tall metal tower, like a multi-story building, with dozens of horizontal trays or packing material inside. The column maintains a constant temperature difference. It's super hot at the bottom, and the higher you go, the cooler it gets. The oil is first heated intensely in furnaces, usually to around 660 degrees Fahrenheit, and then injected into the middle of the column in this hot state. Once inside, the oil starts behaving completely differently than it did in the pipeline. It partially vaporizes, creating a mixture of vapor and liquid. Lighter components with lower boiling points quickly turn to vapor and rise upward. Heavier fractions stay lower or flow all the way down to the bottom. Each level of the column corresponds to its own temperature range, so the vapors condense exactly where they're comfortable. As a result of this process, crude oil is essentially taken apart
where it
into its
remains
components.
hottest, settle
The lightest
lubricating
fractions
oils and
collect at
heavy
the top,
residues.
medium ones below, and the heavy residues remain at the very bottom. Everything happens without chemical reactions. The molecules don't break down or change. They simply separate based on physical properties. It's from this point that the real life of crude oil begins as raw material for fuel, lubricants, and dozens of other products, because each fraction obtained will follow its own technological pathway. This is where diesel fraction first appears. It's heavier than gasoline and kerosene, so it condenses lower down, but it's still light enough to be a liquid fuel. This isn't finished diesel fuel yet, just a halfway point: gas oil. It packs a lot of useful energy, but also plenty of sulfur, nitrogen compounds, and unstable molecules that engines hate. The gas oil that comes out of crude distillation is still miles away from the diesel fuel you pump into your tank. It looks similar, sure, but its makeup is dirty by modern standards. It contains sulfur, nitrogen compounds, traces of metals, and unstable hydrocarbon chains that oxidize easily and form carbon deposits. If you fed this stuff straight into an engine, it would quickly destroy the injectors, catalytic converters, and exhaust cleaning systems. That's exactly why gas oil has to go through a hydro-treating stage. At this stage, the fuel gets channeled into special reactors where they create extremely harsh conditions. Temperature there typically hits several hundred degrees, and pressure runs dozens of times higher than atmospheric. Hydrogen gets fed into the gas oil, and this mixture passes through a catalyst bed. The catalyst doesn't get consumed in the process, but it's what forces the chemical reactions to go fast and in the right direction. Without it, purification would either be way too slow or just flat out impossible on an industrial scale. When the gas oil contacts the hydrogen, a series of reactions kicks off. Sulfur-containing compounds break down, and the sulfur converts into hydrogen sulfide, a gas that's easy to separate from the fuel. Nitrogen compounds transform into ammonia, which also gets removed from the stream. At the same time, hydrogen heals unstable molecules. Double bonds get saturated, and fragile structures rearrange into more stable ones. As a result, the fuel becomes chemically calmer, oxidizes less during storage, and behaves better during combustion. After the reactor, the gas oil is cooled and sent to separation units. There, gaseous products, hydrogen sulfide, ammonia, excess hydrogen, are separated from the liquid fuel. Hydrogen is usually recycled back into the process, while harmful gases are sent for further processing or neutralization. It's thanks to this stage that sulfur content in diesel fuel drops by tens or even hundreds of times, down to levels that meet modern environmental standards. The importance of hydrotreatment can't be overstated. It doesn't just cut harmful emissions, it directly impacts engine life. Cleaner fuel puts less wear on fuel injection systems, doesn't poison catalytic converters and particulate filters, burns more consistently, and keeps the engine running predictably. This is really the stage where gas oil stops being a semi-raw material and starts becoming actual diesel fuel suitable for 21st century machinery. But the process doesn't end there. Some diesel components don't even come from primary distillation. Heavy petroleum residues go through vacuum distillation, where reduced pressure extracts even more useful fractions. And if that's still not enough, cracking enters the picture. A process where large, lazy molecules are literally broken down into smaller ones. Hydrocracking is especially critical for diesel because it produces fuel with better combustion characteristics, a higher cetane number, and fewer impurities. After all these stages, different diesel components get blended together. This isn't some random pouring from one barrel to another. It's precise recipe-based mixing. Engineers dial in the proportions so the fuel meets standards. Good ignition, no thickening in the cold, minimal smoke, and no damage to the fuel system. At this stage, they add additives, tiny amounts, but with big impact. They improve lubrication properties, protect against corrosion, reduce foaming, and help the engine start up in winter. Seasonality is a whole different story. Summer diesel is thicker and more stable in warm temperatures. Winter diesel undergoes additional processing. Components that could crystallize in the cold are removed or modified. Otherwise, at 14 degrees Fahrenheit, the fuel starts turning into a cloudy sludge that clogs the filters. For extremely cold regions, they make Arctic diesel, lighter, pricier, and way more complex to produce. Once the fuel's ready, it's stored in tanks, then shipped to fuel depots, and finally to gas stations. But even along that route, it can still be tested, filtered, and adjusted. Diesel isn't a product where you can afford close enough. One small mistake at the refinery can turn into widespread equipment failures. Let me show you something incredible. This is a substance that weighs more than lead, gold, or any other metal on the periodic table. We're in Oregon, at a unique facility where they purify and process osmium. It's the 76th element that most people have never heard of in their lives, and that's a real shame. Osmium is like the introvert of the chemistry world. It's so rare and specific that most people simply don't encounter it in everyday life. This is extreme physics at its finest. Ready to see this cosmic stuff with your own eyes? Then let's go inside. First thing they told me walking in, don't touch anything with bare hands. Not because it's expensive, though it's expensive too, but because osmium in certain forms releases a compound that irritates mucous membranes and in sufficient concentration can damage your retina. It's called osmium tetroxide. So everyone here wears gloves, and the ventilation here is more serious than in a hospital wing. Great way to start a tour, right? But I'm already inside, cameras rolling, and there's no backing out now. Wish me luck. Now for the numbers, because without them, I don't understand why anyone would even mess with this stuff. Osmium melts at 5,486 degrees Fahrenheit. It's the highest density of all known elements. A matchbox with a volume of about 3 cubic inches, if you made it entirely from osmium, would weigh around 12 pounds. 12 pounds. That's like a small bag of groceries, only the size of your palm. I held a sample like that once. The feeling's bizarre. Your brain's telling you something this size can't weigh this much, but your hand's absolutely not buying it. It's one of those moments where the number in the textbook and the actual sensation in your palm are two completely different things. Another number worth keeping in mind, osmium's melting point, 5,521 degrees Fahrenheit. It's the third hardest metal after rhenium and tungsten among refractory elements, way higher than steel, which melts somewhere around 2,000 degrees. In practical terms, you can't melt osmium in an ordinary industrial furnace. Period. That's why they don't make ingots here, and they don't cast parts like at a regular metallurgical plant. The whole process takes a different route. More on that in a bit. Where does osmium come from? You don't find it like iron. No quarries or mines. Osmium's a byproduct of processing nickel and copper ore. Deep in the mines of South Africa or Canada, they're extracting nickel ore, and osmium just happens to be present in trace amounts alongside platinum, palladium, and iridium. Concentration, 1 to 10 parts per billion. To get a single pound of osmium, you need to process 500 to 1,000 tons of raw ore. That's why the market price sits between $1,500 and $2,000 per troy ounce. For comparison, gold currently runs just over $2,000 per troy ounce. Osmium is nearly neck and neck with it price-wise. The raw material arrives at this facility as osmium-bearing concentrate, a grayish-black powder packed in sealed stainless steel containers. The containers are small, about the size of a coffee can. Inside might be 2 to 5 troy ounces of material. Each one of these cans represents $3,000 to $10,000 of raw material. They arrive in a regular courier van, but with paperwork running several pages and cargo insurance. The exact amount isn't disclosed publicly, but from the manager's expression, it's clear the figure is substantial. And a small sample taken for incoming analysis. Literally a few milligrams of powder that go into a spectrometer. If the composition doesn't match the documentation, the batch gets returned. No discussion. First purification stage, dissolution. The concentrate goes into a reactor with an acid mixture at around 350 degrees Fahrenheit. Osmium converts to gaseous tetroxide during this process, the very compound they warned me about at the entrance. This gas is immediately captured and absorbed by a specialized solution in a sealed tube system. Zero external leakage. The system gets checked for integrity every morning before startup. Next, chemical reactions convert the osmium back into solid form and store it as what's called osmium sponge, a porous dark powder containing approximately 95% metal. This whole process takes 6 to 10 hours per batch, and there's no rushing it. The reaction proceeds at its own pace, and nobody tries to speed it up. The second stage is hydrogen reduction. The osmium sponge gets placed in a tube furnace, through which hydrogen is passed at a temperature of 1100 degrees Fahrenheit. The hydrogen picks up residual oxygen impurities, and what comes out is metal powder with a purity of 99.9%. This takes another 4 to 6 hours. The tube furnace looks completely ordinary, a metal tube about 3 feet long, hooked up to a gas line. If you didn't know what was happening inside, you'd think someone was just drying laundry. But inside this tube, the powder transforms from a dirty concentrate into one of the purest metals produced commercially in the United States. Stage 3 is pressing and sintering. The powder gets loaded into a steel die and pressed at roughly 3,000 pounds per square inch. You get a small cylinder, about 1 inch in diameter and half an inch tall. Looks like a coin, only thicker and darker. Then this cylinder goes into a separate furnace, this time at 2000 degrees Fahrenheit, where the powder particles fuse together into a solid metal. After sintering, the density of the sample is already 22.5 grams per cubic centimeter, very close to the theoretical maximum for this metal. Shrinkage during sintering runs about 15% of the original volume, and you've got to factor that into your calculations ahead of time, because the die has to be created with extra room for exactly that shrinkage. After sintering, each sample is weighed and measured. Weighing here isn't just a formality. The scales are accurate to 1,000th of a gram, because at these metal prices, losing even a few hundredths of a troy ounce is real money. All trimmings, all leftover powder, all fine dust from under the press, collected and returned to the recycling loop. Nothing gets thrown away. Even the wipes used to clean work surfaces go to regeneration. They might contain a few micrograms of metal too. Where does finished osmium go? One application: nibs for premium fountain pens. Osmium is incredibly hard and wear-resistant, so a pen like this can write for decades without noticeable tip wear. That's why you'll see Oz marked on expensive pens next to the manufacturer's name. Another application: electrical contacts in relays and measuring instruments, where you need longevity through millions of cycles, and where ordinary copper or silver wears out faster. And the third area, one they talk about more carefully here, medical implants. Osmium combined with iridium creates an alloy of exceptional hardness, used to make pacemaker components and certain orthopedic devices. The human body barely reacts to this alloy. It's biologically neutral, which in medicine is extremely expensive in the most literal sense. The details of contracts with medical manufacturers, those aren't disclosed here. I asked how much finished metal they produce per month. The answer: 20 to 50 troy ounces. That's 4 to 10 pounds of metal over 30 days of operation. Sounds ridiculously small. But in terms of value, $30,000 to $100,000 monthly from a single facility of this size. And there's a backlog of orders 3 to 4 months out. Demand is steady, supply is limited by nature itself. There won't be more ore, and the number of facilities worldwide that actually know how to handle this metal properly, you can count them on one hand. What do you think will happen when osmium runs out? Drop a comment, because I can't stop thinking about it. But your hand feels something fundamentally different from anything I've held before. Your brain refuses to believe it, but physics doesn't ask permission. That's the whole difference between knowing the number and feeling it in your palm. 12 pounds in your fist, and 0 special effects.
There is a metal so rare that if you ground up the entire crust of the Earth, you'd find about 1 atom of it for every billion atoms of rock. 1 in a billion. The whole planet has produced only a few thousand tons of it in all of human history, and almost every gram is fought over by a handful of companies you've never heard of. No mine on Earth digs for it on purpose. It comes out by accident as a ghost hiding inside copper. And here's the thing nobody tells you. Without this one metal, not a single modern fighter jet would leave the ground. The F-22, the F-35, the engines that push them past the speed of sound, all of them depend on a substance rarer than gold and harder to melt than almost anything in nature. Watch to the end, because the way they turn it into a jet engine blade breaks a rule you were taught in school. They grow a single piece of metal as one perfect crystal. And if they get it wrong by a fraction, the blade tears itself apart at 30,000 feet. Let's start with how rare this thing actually is, because the numbers don't feel real. The metal is called rhenium, symbol Re, number 75 on the periodic table. And it is one of the last stable elements that humans ever discovered, because there was so little of it that nobody could find it. In the Earth's crust, it sits at about 1 part per billion. To put that in plain terms, gold is roughly 5 times more common than rhenium. Platinum, more common. There is no rhenium mine. There is no vein of it in the ground you can follow. It does not even like to form its own rock. The entire world digs up somewhere between 40 and 50 tons of it a year. And that's it. That's the whole global supply, 40 tons. You could fit a single year's worth of the metal that flies every fighter jet on Earth into the back of a couple of pickup trucks. And it gets stranger because nobody actually goes looking for it. They find it while hunting for something else entirely. Here's where it comes from: copper and molybdenum, that gray metal they put in steel to make it tough. All over the world, in places like Chile, the United States, and Peru, there are giant open-pit copper mines. Holes in the ground so wide you can see them from space. They blast the rock, haul it out by the truckload, and crush it to get the copper. But buried inside that ore, in a mineral called molybdenite, there are a few atoms of rhenium scattered through it, sometimes as little as 2 parts in 1,000. When they roast the molybdenite to purify it, the rhenium boils off as a gas, drifts up the chimney. They run the smoke through scrubbers and filters, trap the fumes, and pull the rhenium back out of what was basically pollution. Think about that. The metal that flies the most advanced aircraft ever built is recovered from the exhaust of a copper smelter. It is, quite literally, scraped out of the smoke. And out of every truckload of ore, you might get a fingernail's worth. So why go to all that trouble? Why fight over a few tons of gray metal scraped out of a chimney? Because of one number. Rhenium melts at 3,186 degrees Celsius. Let that sink in. Steel turns to liquid at around 1,500. Most metals are long gone before you get near rhenium's melting point. Out of every element in nature, only tungsten holds out longer against heat. And inside a jet engine, heat is the entire problem. When a fighter jet's engine is running at full throttle, the gas blasting through the hot section reaches around 1,470 degrees Celsius. Here's the insane part. That gas is hotter than the temperature at which the engine's own metal blades start to melt. The fire moving through the engine is hotter than the metal that's supposed to survive it. By every rule of physics, those blades should turn to liquid, and the engine should destroy itself in seconds. And yet, they don't. They spin tens of thousands of times a minute for thousands of hours in a furnace hotter than their own melting point. Rhenium is a big part of why. Now here's the part that breaks the rule from school. Take a normal piece of metal, a steel bar, a copper pipe, anything. Look at it under a microscope and you'll see it's not one solid thing. It's made of millions of tiny crystals called grains packed together like a bag of gravel. And the lines where those grains meet, the grain boundaries, are the weak spots. Under enough heat and force, metal slowly stretches and creeps along those boundaries until it fails. Inside a jet engine, where the blades are spinning hard enough to feel a force thousands of times their own weight, in heat past their melting point, those boundaries are a death sentence. So the engineers did something that sounds impossible. They got rid of them. They grow each turbine blade as a single crystal, one. The molten superalloy, packed with rhenium, is poured into a mold and cooled with brutal precision, pulled out of the furnace so slowly that the metal solidifies as one continuous crystal from bottom to top, with no grains and no boundaries anywhere inside it. A single blade, no bigger than your hand, is one unbroken crystal of metal, and rhenium is what makes it survive. The rhenium atoms are huge and they move incredibly slowly, so they jam up the inside of the metal, locking it in place and stopping it from creeping under the heat. A blade with 3 to 6% rhenium can take temperatures 60 degrees higher than one without it. 60 degrees that decides whether a fighter jet flies or falls. So where does all this go? Into the hottest, most punishing place in any aircraft, the high-pressure turbine, right behind the flame. The F-15 and F-16 fly on blades with about 3% rhenium. The newer ones, the F-22 Raptor and the F-35, use single crystal blades with 6%. The third generation, the best money and chemistry can build. The same alloys spin inside the engines hanging under commercial airliners, the CFM engines that move millions of people across oceans every single day. Every one of those blades was grown as one crystal, seeded with a metal scraped out of copper smoke. A metal so scarce the entire world makes less of it in a year than a steel mill makes before lunch. And that's the strange truth of rhenium. 70% of everything ever produced gets melted into these blades and bolted into the fire of a jet engine, where it'll spin past the speed of sound and never be seen by the people whose lives depend on it. Nobody minds it. Nobody plans for it. It falls out of the sky as smoke from a copper plant, and it ends up holding the fastest machines humans have ever built together against a fire hotter than the metal itself. If this changed how you see what's hiding inside a jet engine, hit subscribe, and I'll show you the next material most people never even know exists.
Every year, machines are built around the world so massive and powerful that a single one could supply electricity to an entire city, and costs as much as dozens of private jets. But what if I told you that inside this colossal structure, there are parts machined with precision, thinner than a human hair, and that one tiny mistake could cost millions of dollars or even destroy everything? Today we're going inside a place almost no one gets to see, the heart of turbine manufacturing. And trust me, what you're about to see will completely change how you think about engineering, if you stick around till the end. Let's start with the fact that there are two main types of these turbines, and they work on very different principles. First, the steam turbine. You'll find these at nuclear and thermal power plants, on massive tankers and icebreakers. Second, the gas turbine. It's more like a giant jet engine without wings, and lives mostly at gas-fired power plants and on some military vessels. Here at the factory they make both types, but we're heading first to the steam ones, because they're older, more massive, and look like they were invented 2 centuries ago. Which, actually, they were, but they're still very much around. How a steam turbine works, short and formula-free. There's a boiler that heats water into pressurized steam at anywhere from 800 to 3,000 pounds per square inch. This steam, hot, pressurized, angry, blasts through nozzles onto rotor blades. The blades start spinning. The rotor spins the shaft. The shaft spins a generator or a ship's propeller. The steam cools down, condenses back into water, and returns to the boiler. The cycle is closed. Sounds simple, but for this simple not to explode into pieces and to run for 3 years without major repairs, you need all of this around me. The first shop they take me to is the foundry. This is where every turbine begins. The casing, the outer shell that holds all the internal components under pressure, is cast from alloy steel or cast iron, depending on operating parameters. For steam turbines in large power plants, the casing is cast in 2 or 3 tiers, and each tier is a separate mold. The mass of 1/2 of a casing can reach 60 to 80 tons. The metal is melted in arc furnaces with a capacity of 50 to 150 tons of molten metal, and the temperature there is around 5,000 degrees Fahrenheit. The mold for a large casing is a pit in the floor, 6 to 10 feet deep, lined with refractory clay. The metal is poured through a system of channels, and the entire process of filling one large mold takes 15 to 30 minutes. Then the casting cools, naturally from several days to 2 weeks, depending on the mass. After cooling, the casting goes to its first inspection. Ultrasonic testing searches for voids and inclusions inside, spots where the metal didn't fuse the way it should. X-rays check critical zones. If they find something significant, the casting goes back to remelt. No compromises. The rejection rate at this stage runs 3 to 8% depending on the casting's complexity, and that's completely normal for parts this size. Next, machining. Now, here in the shop floor, there are machines that made my jaw drop. The horizontal boring mill that machines the inner casing surface. It's about 60 feet long. The table where the part sits moves. The spindle stays put. The tool freely bores the bearing and seal mounting surfaces to an accuracy of plus or minus half a thousandth of an inch. Why so precise? Because the rotor spinning inside at 1500 to 3600 revolutions per minute has a clearance between its blades and the casing of 50 to 150 microinches. 1% efficiency loss at a large power plant. That's millions of dollars in extra fuel costs per year. The rotor is the star of this story. It's a shaft carrying discs with blades, and it's the most complex part of the entire turbine. The shaft for a large steam turbine is a forging made from special chromium molybdenum vanadium steel, 20 to 40 feet long and weighing 20 to 60 tons in its rough state. A forging means you take a red-hot ingot of metal and just hammer it with a press weighing 5,000 to 50,000 tons to give it the shape you need. The grain structure of the metal during forging gets oriented along the shaft's axis. That's how you achieve torsional strength. After forging, the shaft goes through heat treatment again, then heads to the machine shop. Turning takes 2 to 4 weeks of continuous work on a lathe that's nearly 70 feet long. Chips fly, coolant flows, and machining away from that massive blank reveals the sleek shaft you saw in the drawings. This is the part where I'm always amazed. A gigantic component, yet precision like a watch mechanism. Blades are a separate production line. Steam turbines at large power plants have anywhere from 8 to 20 stages, and each stage is a disc with blades. First stage blades are small, sometimes less than 2 inches tall, because the steam there is still under high pressure and dense. Last stage blades are massive, up to 5 or 6 feet long on the largest turbines. These blades are forged and milled from iron-based alloys or stainless steel, and in their final profile, they have an aerodynamic shape with precision to within plus or minus 2/1000ths of an inch along the entire length. Each blade is checked for resonant frequency. It can't match the operating rotational frequency of the rotor, or else after a few thousand hours, a fatigue crack will develop from vibration. How they test this is simple. They tap the blade with a small hammer and listen with a special acoustic sensor. A very elegant method for such a serious problem. Assembling the rotor. This is when it starts to feel like an operating room. Bladed discs get mounted onto the shaft using shrink fitting. The disc gets heated to 300 to 400 degrees Fahrenheit. It expands, slides onto the shaft, then cools and grips the shaft with a force no bolt could ever match. No threads, no glue, just temperature difference and precision sizing. The interference fit when cold, 1 to 3/1000ths of an inch per inch of diameter. After assembly, the rotor gets balanced, and this takes 1 to 3 days. Balancing happens on a specialized rig, where the shaft spins on bearings while sensors register vibration. If there's any imbalance, metal gets removed from certain spots, or balancing inserts get installed. Allowable residual vibration on a large rotor, fractions of an ounce per inch of radius. If you think that's strict, you're thinking right. After assembly, the turbine heads to the test stand. At full operating parameters, pressure and temperature, they run the turbine for 24 to 72 hours. Sensors track bearing temperatures, vibration, steam leaks, power output. If anything goes outside the limits, stop, disassemble, analyze. There have been cases where they found a defect here that the X-ray missed initially. So the test stand isn't just a formality. It's the last line of defense before shipping. The finished turbine gets broken down into transport blocks, casing separate, rotor separate, auxiliary equipment separate. A large turbine rotor travels on a special trailer with hydraulic suspension, the kind you've seen on YouTube, with 18 axles moving at 20 miles per year. They coordinate the route a month in advance. Every bridge height and every turn width needs checking from the factory to the port or customer. Sometimes for one of these transports, they temporarily remove road signs and even take down power lines over the highway. I asked the chief engineer how many turbines they build per year. He said 12 to 20 of various types. That's it. Less than 2 per month. But each one runs for 30 to 50 years and generates electricity for hundreds of thousands of people every day. Some things don't need high-volume production. What if one of the most common metals on Earth has a hidden property that even some engineers still underestimate? A metal that boils like water and vanishes into thin air during production, only to be reborn as gleaming ingots. We see it every day, but almost no one knows what the underground cities where it's mined look like, or what giant machines make the ore ignite like little controlled earthquakes. In this video, you'll discover things you never suspected, and by the end, the main secret will be revealed that will forever change how you think about zinc. Zinc is the 4th most consumed metal in the world, right after iron, aluminum, and copper. That alone tells you just how critical it is for the global economy and industry. Annual worldwide zinc production runs somewhere between 12 and 13 million metric tons. We're talking massive volumes here, which really drives home how irreplaceable this metal is across hundreds of different applications. The main zinc mining regions are China, Australia, and Peru. These 3 countries together account for a huge chunk of global zinc ore production, making them the key players in the market. For instance, China isn't just the world's largest producer, it's also the biggest consumer of zinc, which reflects its massive industrial growth. Other major producers include India, the United States, Mexico, and Canada. As for reserves, the U.S. Geological Survey estimates that global zinc reserves sit at around 250 million metric tons. Beyond that, there are what we call resource bases, essentially potential deposits that haven't been fully explored yet, or aren't economically viable to mine right now. These are estimated at over 1,800 million tons. These numbers tell us that zinc, unlike some rare metals, will be around for many decades to come, even with consumption on the rise. The biggest user of zinc is the galvanizing industry, which uses it to protect steel from corrosion. This sector accounts for roughly 60% of all zinc produced. This shows just how critical zinc is for construction, automotive manufacturing, infrastructure production, and countless other industries where steel's strength and durability are essential. Without zinc coating, the lifespan of steel products would drop dramatically, leading to massive economic losses and a huge spike in resource demand. 15 to 20% of zinc is used to produce alloys like brass and die-casting alloys. These alloys are used in making parts for cars, household appliances, toys, plumbing fixtures, and electronics. Another 10 to 15% goes into making zinc oxide and other chemical compounds. Zinc oxide has a ton of uses, from sunscreens and cosmetics to paints, ceramics, the rubber industry, and even animal feed supplements. Its antibacterial and protective properties make it a versatile ingredient. The rest of the zinc goes into battery production, as a micronutrient in agriculture to boost crop yields, and in pharmaceuticals and dietary supplements, since zinc is essential for the human immune system. When it comes to pricing, like most commodities, zinc prices fluctuate based on global supply and demand, economic cycles, and the situation in major producing and consuming countries. However, demand for zinc remains stable or growing, driven by urbanization, infrastructure development, and the worldwide need to protect metals from corrosion. This makes zinc an important indicator of global economic health. Most zinc is extracted from underground mines. These are entire underground cities stretching hundreds of feet and sometimes several miles beneath the Earth's surface. We're not talking about simple holes in the ground. These are networks of tunnels, shafts, ventilation systems, and hoisting structures. It all starts with exploration. Geologists work like detectives, searching for what's called ore bodies, sections of rock where the concentration of zinc is high enough to make mining it profitable. Now, zinc typically shows up as a sulfide ore, like sphalerite, and it almost always comes bundled with lead, silver, and sometimes copper. Once they've located a deposit, the real work begins: building the mine itself. This involves sinking vertical shafts that serve as the main access points for getting to the ore, hauling materials up and down, and moving equipment in and out. They also create horizontal tunnels, what miners call drifts, that lead straight to the ore veins. The actual ore extraction is where things get dynamic and risky. Miners bring in specialized gear, powerful drilling rigs that bore holes into the rock face, called blast holes. These holes get packed with explosives. Then comes the carefully controlled blast that breaks apart massive volumes of rock. Think of it like a controlled earthquake on a smaller scale. Dramatic, but completely under control. The dusty air is quickly removed by powerful ventilation systems, which also bring fresh air deep underground. The blasted ore is then loaded into massive underground haul trucks or onto conveyor belts using heavy-duty loaders. It's like a non-stop underground highway, constantly moving tons of ore to the main hoisting shafts. From there, the ore is lifted to the surface using powerful elevators or specialized conveyor systems that climb hundreds of feet vertically. At every stage, from drilling to hoisting, strict safety protocols are followed because working underground demands maximum caution. Once the ore reaches the surface, it still looks like ordinary rock containing only a small percentage of zinc. To extract the valuable mineral, the ore goes through a processing plant, a whole complex of sophisticated processes. The first step is crushing and grinding. Massive chunks of ore feed into crushers that break them down into smaller pieces with a deafening roar. This crushed ore then goes into ball or rod mills, giant rotating drums filled with steel balls or rods. Inside these mills, the ore gets ground down into an extremely fine powder, almost like flour. This is critical to free the zinc mineral crystals from the surrounding rock. The next key stage is flotation. The ground ore powder gets mixed with water and special chemical reagents in large tanks called flotation cells. These reagents selectively stick to the zinc mineral particles, making them water repellent. Then air is pumped through this mixture, creating millions of tiny bubbles. Particles of zinc mineral latch onto these bubbles and float up to the surface, creating foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. That's your zinc concentrate, which can pack up to 60% zinc. Since zinc often hangs out with lead, the plant might run several flotation cycles to separately pull out zinc concentrate from lead concentrate. The zinc concentrate you get, it's still not pure metal. It's got to go through metallurgical processing to turn into actual metallic zinc. And this is where we enter the world of extreme temperatures. If they're using the pyrometallurgical method, the zinc concentrate first gets roasted. The concentrate is heated in special furnaces at around 1,800 degrees Fahrenheit. This burns off the sulfur that's part of the sulfide ore, converting it into zinc oxide. During this process, the sulfur transforms into sulfur dioxide gas, which gets collected and used to produce sulfuric acid, a crucial industrial product. This not only cuts down on air pollution, but also creates an additional valuable byproduct. Next, the zinc oxide gets mixed with coal and heated to even higher temperatures, over 2,200 degrees Fahrenheit, sometimes reaching as high as 2,700 degrees, depending on the specific furnace technology. At these extreme temperatures, a reduction process takes place. The carbon strips away oxygen from the zinc oxide, releasing pure metallic zinc. And here's where that amazing evaporation effect happens. At these temperatures, the metallic zinc transitions into a gaseous state. Basically, it evaporates. Zinc has a relatively low boiling point compared to other metals. So in these furnaces, where the temperature is way higher, zinc literally turns into vapor that rises up and gets captured in special condensers. There, the vapor cools down and condenses, turning back into liquid metallic zinc. This liquid zinc is then poured into molds to create ingots or pellets. What if the metal that still powers most cars on the planet has been quietly poisoning people since the days of the Roman Empire? And we found out too late. Lead-built aqueducts adorned the faces of Egyptians, and today hides in billions of lead-acid batteries, without which cars, elevators, and entire cities would grind to a halt. We'll descend into mines where explosives shatter rock, trace the journey of galena to red-hot furnaces, and discover why this metal simultaneously saves infrastructure and destroys health. Stick around till the end. One fact about lead will forever change how you look at an ordinary battery. Okay, let's rewind the clock and dive into a story that began long before the first smartphones and even before the invention of the wheel. How did people even learn about lead, this sneaky, two-faced metal? Truth is, nobody knows exactly who or when first discovered lead, because it wasn't officially discovered by a scientist in a lab like many other elements. Lead is one of those metals that's just always been around humans, and its history is intertwined with the history of civilizations themselves. Picture this: ancient times, way before people learned to work with iron, or even copper. They were searching for interesting stones, clay, anything they could use. And then, in certain places, especially where there are ore deposits, they stumbled upon a really unusual stone. These were lead ores, most commonly galena, lead sulfide, which looks like dark gray, almost black crystals with a metallic shine, often in cubic shapes. Lead ores often lay close to the Earth's surface, and there was plenty of it around. Plus, lead sometimes occurs in its natural, pure form, though that's pretty rare. Lead has an incredibly low melting point, just 621 degrees Fahrenheit. This means you didn't need some super high-tech furnace to melt it down. A good hot campfire was enough, and if there happened to be lead ore nearby, shiny liquid metal could literally just melt right out of it. The metal in the ore heats up, melts, and starts flowing out of the rock, forming little shiny puddles or droplets. This must have been absolutely mind-blowing to witness. Out of stone, without any tools, just from fire alone, this shiny, heavy, soft material appears that you can shape with your hands. You could easily flatten it, bend it, cut it even with primitive tools. It wouldn't break like stone. This made it perfect for crafting simple objects. Archaeological findings show that lead was used as far back as 7,000 or 8,000 years ago, dating to the Neolithic period, for example, in Turkey. People found beads and other small lead objects there. In Mesopotamia, Egypt, and later in Greece and Rome, lead became widespread due to its availability and ease of working with. The Romans built their famous aqueducts and water supply systems using lead pipes. The word plumbing comes from the Latin plumbum, which means lead. Ancient Egyptians used lead sulfide for eye makeup, while Romans used it for skin lightening and in paints. Nobody back then, of course, suspected this metal was toxic. After all, lead poisoning symptoms were often chronic, developed slowly, and could easily be blamed on bad luck, other illnesses, or curses. People just saw a shiny, useful metal that was easy to work with, and they actively used it, never suspecting that beneath its appeal lurked a treacherous enemy. Now that we know the grim history of lead's discovery, let's fast forward to our time. Despite all its toxicity and the massive campaign to phase it out, lead is still part of modern industry. But how is it mined now, and where does it hide when we're so desperate to get rid of it? This is a story about precision, control, and the constant battle against its poisonous nature. Lead, like its neighbor zinc, is rarely found in its pure form. It's mostly extracted from ores, where it exists as lead sulfide, known as galena. And, as you might have already guessed, this anti-hero often shares its deposits with zinc, as well as other valuable metals like silver and copper. The world's top lead producers are China, Australia, the United States, and Peru, which once again overlaps with the geography of zinc mining. The extraction process starts with locating ore bodies. Geologists, armed with cutting-edge technology, scan the ground and conduct exploratory drilling to find spots where galena concentrations make economic sense. Once a deposit is identified, mining operations begin. This can either be an open-pit mine, where massive excavators strip away the top layers of earth, gradually working their way down to the ore, or an underground mine, where miles of tunnels are drilled, penetrating deep into the Earth's crust. In underground mines, drilling rigs are used to create holes in the rock, which are then packed with explosives. After controlled blasts that break up the ore vein, specialized loaders gather the ore fragments and haul them to the hoisting shafts. Ventilation systems run at full capacity, removing dust and pumping fresh air down into the depths. All the ore is brought to the surface, where it begins its long journey to becoming a metal ingot. After crushing, the flotation process kicks in. This is a chemical-physical method that separates different minerals. The crushed ore is mixed with water and special reagents in massive tanks. These reagents selectively attach to galena particles, making them water repellent. Then air is pumped through the mixture, creating bubbles that the lead mineral particles cling to and rise to the surface as foam. This foam is collected, forming lead concentrate. The waste rock settles at the bottom and gets disposed of. Since lead and zinc are often found together, different reagents and flotation cycles can be used to separate them individually, which requires high precision and chemical control. The resulting lead concentrate, now containing a much higher percentage of lead, is shipped to the metallurgical plant. This is where it transforms into pure metal. The most common method is pyrometallurgy, which involves several stages. First, the concentrate is roasted in special furnaces at high temperatures. This is a calcination process that removes sulfur from galena, converting it into lead oxide. The sulfur that's released as sulfur dioxide gas is carefully captured and converted into sulfuric acid to prevent air pollution. Then the lead oxide is loaded into large blast furnaces, where it's mixed with coke and fluxes. In these furnaces, at temperatures over 2,000 degrees Fahrenheit, a reduction process takes place. The carbon from the coke pulls oxygen away from the lead oxide, releasing liquid metallic lead. The molten lead, which is extremely heavy, settles to the bottom of the furnace. On top, a layer of slag forms. That's the melted impurities. Molten lead is periodically drained from the furnace, but this isn't pure lead yet. It contains impurities of other metals, such as copper, silver, gold, bismuth, and nickel. That's why lead goes through one more stage, refining. This could be heating to specific temperatures to remove impurities, or electrolytic refining, where electric current separates lead from other metals, achieving very high purity. It's at this stage that valuable byproduct metals like silver and gold, which accumulate in lead ores, are extracted. So where is all this carefully mined and refined lead being used today, now that we know about its dangers? The biggest consumer of lead, accounting for about 85% of all global consumption, is the production of lead-acid batteries. These are the same batteries that start the engines in nearly every car on the road, and they're also used in uninterruptible power supplies, backup power for telecom networks, and large-scale energy storage systems. In electric vehicles, even though the main battery is lithium-ion, there's often still a small 12-watt lead-acid battery to power the onboard electronics. This is a massive market that keeps demand for lead rock solid. Your house has no electricity. Your phone doesn't exist. The internet is physically impossible. Electric motors of any kind can't be built. And human civilization is frozen in the 1800s with steam engines and gas lamps. All because we never figured out how to refine one reddish metal that conducts electricity better than anything else except silver, which costs 50 times more. Without this metal, every wire would need to be 3 times thicker and cost 4 times as much. Power grids couldn't reach beyond cities. Your electric bill would be $1,200 monthly. Today, we're going inside the factory in Utah, where this metal gets refined to 99.99% purity. And I'll show you why that purity matters, and what would happen if we used something else instead. The Kennecott Copper Refinery in Magna, Utah, sits 12 miles west of Salt Lake City, and has processed copper continuously since 1903. This facility receives ore from Bingham Canyon Mine 20 miles south, the largest man-made excavation on Earth visible from space. The refinery processes 300,000 tons of copper per year, and every step creates properties that make electrical civilization possible. Raw copper ore contains only 0.6% actual copper mixed with rock and minerals. If copper was never discovered, we'd use aluminum for electrical wiring. Aluminum conducts only 60% as well as copper, meaning you need 50% more cross-sectional area for the same current. Every wire in your house would be thicker and heavier. Building construction costs would increase 30% just from wiring. The first stage crushes ore into powder and mixes it with water and chemicals in flotation tanks. Air bubbles blow through, and copper minerals stick to bubbles and float as froth while waste rock sinks. The froth contains 30% copper, a 50-fold increase from raw ore. This concentration matters because copper's conductivity depends entirely on purity. Even tiny impurities dramatically increase resistance. 1% phosphorus increases resistance by 50%. 0.1% arsenic doubles it. Without purification, we'd use metals that lose huge amounts of energy as heat. Power companies would generate 3 times more electricity just to compensate for transmission losses, 3 times more power plants, fuel, and pollution. Concentrated ore moves to the smelter and heats to 2,200 degrees Fahrenheit. Copper melts and separates from sulfur and iron, which become slag. What emerges is blister copper at 98% purity. Better, but not good enough for electrical use. Copper's heat tolerance becomes important here. It carries high currents without melting, doesn't melt until 1,984 degrees Fahrenheit. Aluminum melts at only 1,221 degrees. In electric vehicle motors or transformers, aluminum would literally melt under load. Electric motors would need to be 3 times larger to keep current densities low enough. A 200-pound copper motor would weigh 600 pounds in aluminum and deliver less power. Blister copper moves to electrolytic refining, the most critical stage. Impure copper sheets become anodes in giant tanks with acidic copper sulfate solution. Pure copper cathodes sit opposite, and when current passes through, pure copper ions migrate to cathodes while impurities fall to the bottom. After 12 days, cathodes are coated with 99.99% pure copper. This extreme purity creates extreme conductivity. At 99.99%, copper conducts so efficiently that a mile-long wire loses only 2% power as heat. At 98% pure, that wire loses 15%. With aluminum at any purity, you lose 5 to 8%. The United States has over 600,000 miles of high-voltage transmission lines. If those were aluminum instead of copper, we'd lose 200 billion kilowatt-hours per year in transmission, enough to power 20 million homes. Your electric bill would triple. Pure copper cathodes get melted and cast into forms. Some become wire rod drawn through progressively smaller dies, creating wire from thick power cables to hair-thin magnet wire. Others get rolled into sheets for circuit boards and building materials. Each application requires different properties, but all depend on 99.99% purity. Copper's combination of conductivity and ductility becomes critical here. Copper can be drawn into micron-thick wire without breaking. Aluminum is brittle. When you bend aluminum wire repeatedly, it cracks. This is why every electric motor uses copper windings. The wire bends around tight curves hundreds of times during manufacturing without breaking. Without copper, we couldn't mass-produce electric motors. No motors means no electric vehicles, power tools, washing machines, fans, or pumps. Every copper batch goes through rigorous testing, and there's a specific reason purity standards are so strict. During the 1960s and early 70s, copper prices spiked, and builders used aluminum wiring in homes to save money. Aluminum was cheaper, but had higher resistance, running hotter under load. The real problem was connections. Aluminum expands and contracts more than copper when heating and cooling. Over months of electrical cycling, aluminum wire worked loose from connection points. Loose connections create more resistance and heat. The insulation would char and ignite. Between 1965 and 1973, tens of thousands of house fires traced back to aluminum wiring. Dozens died. Insurance companies refused to cover homes with aluminum wiring. That crisis proved copper can't be substituted. Today, every copper product goes through conductivity testing. Pure copper at 20 degrees Celsius has conductivity of 58 million Siemens per meter. Anything below 57 million gets rejected and reprocessed. They also do bend testing, thermal cycling, and microscopic inspection. The rejection rate is 6%. Copper that passes inspection ships to manufacturers making electrical wire, motors, and electronics. Kennecott produces 300,000 tons yearly, but global production is 25 million tons because demand is enormous. Without copper, no electrical grid exists as we know it. Thomas Edison tried iron wire for electrical distribution in the late 1800s. It didn't work. Resistance was so high that power couldn't travel more than a few blocks. Without copper, electrical power is limited to buildings with their own generators. No power lines between cities. Every building needs its own coal or diesel generator running constantly. The internet is physically impossible. Fiber optics carry data long distances, but electronics at each end require copper for power and short-range transmission. Data centers use thousands of miles of copper cabling. Without copper, you might have mechanical telegrams, but no electronics, computers, or digital communication. Electric motors don't exist in practical form. Every motor requires copper windings for electromagnetic fields. Aluminum motors are 3 times larger for the same power, overheat easily, and fail quickly. Without copper motors, manufacturing never industrialized beyond steam power. Modern factories don't exist. Every product is more expensive because it's made by hand. Transportation is completely different. No electric trains. You're stuck with diesel locomotives. No electric cars. Tesla doesn't exist because you'd need a 6,000-pound aluminum motor to move a 2,000-pound car. Ships use massive diesel engines instead of efficient electric systems. You've seen how copper ore concentrates from 0.6% to 30% through flotation, how 2,200 degree smelting separates copper from impurities, how electrolytic refining creates 99.99% purity, making efficient electrical transmission possible, and why the aluminum wiring crisis proved copper can't be substituted. If this interested you, subscribe for more deep dives into materials making modern life possible. Thanks for watching.
Pick a single strand of your hair and look at it. Now imagine a thread 5 times thinner than that. So fine you can barely see it on your fingertip. That thread is stronger than steel. Not a little stronger. By weight, more than 10 times stronger. Bundle a few thousand of them together, weave them into a sheet, and you get the skin that wraps the wings of an F-22 and an F-35. The fastest, deadliest fighter jets ever built fly on a material that starts as something soft and white, like plastic yarn. And here's the part nobody tells you. To turn that soft white thread into something that can hold a 40,000-pound jet together at twice the speed of sound, you have to nearly burn it alive. Stay to the end, because the moment the color changes from white to black is the moment a fiber becomes one of the most valuable engineered materials on Earth. And almost nobody has ever watched it happen. Let's start with what this stuff actually is, because the numbers don't feel real until you hold them up against something you know. A single carbon fiber filament is about 5 to 10 microns across. A micron is 1,000th of a millimeter. Your hair runs around 70. So we're talking a thread you literally cannot split with your eye. Now take that thread and pull on it. Aerospace-grade carbon fiber holds a tensile strength of roughly 3 gigapascals. In plain terms, by weight it beats mild steel more than 10 times over. Steel sinks, this floats and shrugs off the load. That combination, almost no weight plus brutal strength, is the holy grail for anyone building something that has to fly. Every pound you cut off an aircraft is a pound of fuel you save, or a pound of missile you can carry. And it all begins with a spool of soft white fiber called PAN, polyacrylonitrile. About 90% of all the carbon fiber on the planet is born from that one white thread. It looks like nothing. It looks like fishing line, but it's the seed of the whole thing. So how do you turn fishing line into something that builds a fighter jet? You torture it with heat, in stages, and the first stage is the one that changes everything. The white PAN fiber gets pulled, slow and steady, through through a series of ovens filled with ordinary air, heated to between 200 and 300 degrees Celsius. That doesn't sound like much next to what's coming, but watch what it does. As the fiber crawls through that heat, held under tension so it can't shrink and curl, its molecules lock together into tight, ladder-like rings. And the color shifts, white to yellow to a deep brown to black. You can see it happen down the length of the oven, like a slow fuse burning in slow motion. This step is called oxidation or stabilization, and it is the make or break moment. Get the temperature wrong by a little, rush the speed, and the whole batch is ruined. Here's the catch that makes this material so rare. Every factory guards its exact recipe. The precise temperatures, the precise tension, the precise speed through the oven are some of the most closely held secrets in the industry. Two companies can buy the same white pan, and one comes out with aerospace gold, and the other comes out with garbage. That single difference is worth billions. Now comes the fire that actually creates the carbon. The black, stabilized fiber leaves the air ovens and enters a sealed furnace with no oxygen at all, just inert gas, because at these temperatures, even a whiff of air would make the fiber simply burn away to ash. Inside, the heat climbs past 1,000 degrees Celsius, and for the highest grades, it pushes toward 2 and even 3,000. Think about that, 3,000 degrees, hotter than molten lava, hotter than most metals can survive. And the fiber doesn't melt, it transforms. Everything in that thread that isn't carbon, the hydrogen, the nitrogen, the oxygen, gets blasted out as gas and driven off. About half the original mass vanishes into thin air. What's left behind is over 90% pure carbon, with the atoms locked into long, tight sheets running the length of the fiber. That alignment is the secret to the strength. The atoms are gripping each other in nearly perfect rows, end to end, so when you pull, you're pulling against the raw bonds of carbon itself. This is no longer plastic. It's no longer yarn. It is a thread of nearly pure crystal carbon, thinner than a hair, that you could hang a small car from. But a single thread, no matter how strong, is useless on its own. You can snap one filament with your fingers. The magic is in the numbers. Those filaments get bundled into what's called a tow, and a single tow can hold 3,000, 12,000, even 24,000 individual fibers running side by side. From there, they get woven, on looms that look almost like an old textile mill, into flat black cloth. Run your hand over it and it feels like dark silk, but it shimmers and it's bone dry and it weighs almost nothing. That cloth still isn't a wing though. To build the skin of a jet, the fabric gets soaked in epoxy resin, layer on layer, the threads turned in different directions so it's strong in every direction at once. Then the whole stack goes into a mold, gets sealed in a vacuum bag, and rolls into an autoclave, a giant pressurized oven the size of a tunnel. Under heat and crushing pressure, the resin flows, the air bubbles get squeezed out, and the layers fuse into one solid piece. Because a single hidden air pocket, one bubble you can't see, becomes a weak spot that could split open under the stress of flight. When it comes out, it's lighter than aluminum, stiffer than steel, and shaped like the exact curve of a fighter's wing. So where does all of this end up, and why should you care? Look at almost anything that flies fast or far today. The F-22 Raptor, the F-35, their wings and skins are packed with this material, around a third of the entire jet by weight. The Boeing 787 that carries people across oceans is half carbon fiber composite, wings and body. And here's the twist on the price. The raw fiber, by the gram, is actually cheap, just a few cents. But by the time you've turned white PAN into pure carbon, woven it, layered it, and cured a flawless, certified, defect-free part stiff enough to survive a dogfight, you're looking at a finished material worth thousands of dollars for every kilogram in the air. And the program that flies on it, the F-35, runs well over $1 trillion across its life. That's the real story of carbon fiber. A thread thinner than your hair, born soft and white, nearly burned to death in 3,000 degrees, reborn as black crystal, and woven into the wings that rule the sky. Next time you see a fighter jet carve across the clouds, remember what's holding it together up there. And if you want to see how the engines that push those jets past the speed of sound are forged, that one's even harder to believe. Keep watching.
In every country, asphalt is just a road. But in Dubai, it's a challenge to nature. Here, air temperatures reach 122 degrees in the shade, while the road surface heats up to 160. Regular asphalt would melt within just a few days, but engineers found a way to make it survive. Polymers that hold their shape even at 176 degrees, geotextile membranes that breathe, and sensors that detect defects before human eyes can spot them. Why don't these roads melt like ice in the sun? And what strange technology did they test to make them actually dry after rain? Watch till the end. The finale will surprise you. Standard asphalt consists of stone aggregate and bitumen, a dark, thick substance that holds the mixture together, making it uniform and strong. However, bitumen has one weakness. It starts to soften at temperatures around 113 degrees Fahrenheit. For countries with moderate climates, this isn't a problem since road surfaces rarely reach such heating levels. But Dubai has completely different conditions. There, summer air can heat up to 122 degrees in the shade, while the road surface under direct sunlight can reach 160 degrees. Under such conditions, regular asphalt would literally behave like warm rubber. It would become soft, start deforming under vehicle weight, and in places simply slide off slopes. Plus, sharp temperature changes between scorching days and relatively cool nights would cause cracks to appear. In countries where occasional short heat waves occur, people might not immediately notice these processes. Sure, we sometimes get 104 degrees in summer, but such temperatures don't last long, and the surface deteriorates slowly, gradually. In Dubai, however, high temperature isn't just present, it's constant and stable for several months. This means asphalt is under continuous stress, and if you don't account for this factor, the road literally won't survive. That's exactly why engineers had to find a solution that would allow asphalt to maintain its shape even under extreme heating conditions. They replaced regular bitumen with modified bitumen, with polymer additives that change its physical properties. Such bitumen holds its shape at temperatures up to 176 degrees Fahrenheit. This means even when the road surface heats up to maximum levels, the material still remains stable, doesn't flow, and doesn't change structure. The difference might seem small at first glance. What's a few dozen extra degrees? But this exact difference makes Dubai's roads smooth, even, and durable, even when it's almost impossible to breathe from the heat around you. So what is this modified bitumen? The process is based on mixing bitumen with polymer additives. Polymers act like a reinforcing network at the molecular level. They stretch the bitumen structure, making it more elastic and heat-resistant. As a result, the asphalt doesn't soften. It maintains stability and shape even when heavy bus or truck wheels press on it for hours. The mixing process also isn't limited to just adding polymers. It's crucial to properly select the stone aggregate composition. Stones of different sizes create a framework-like structure, and bitumen here acts not as the main material, but rather as what connects the elements together. If the aggregate is selected incorrectly, bitumen will have to take on too much load, and even the modified mixture will lose stability. Therefore, asphalt composition is always a precise calculation of material ratios that don't just connect, but work as a unified system. But asphalt is just the surface. Hidden beneath it is a multi-layered sandwich that determines the road's durability. The first layer is sand, but regular sand won't work. It's mobile, can shift, and the road would lose its evenness within months. So sand is stabilized by mixing it with cement or special substances that make the mixture less mobile. Next comes a crushed stone layer that provides hardness and distributes load. Special geotextile fabrics can be laid between layers, preventing settling and material mixing. Geotextile works as a membrane that allows water to pass through, but doesn't let soil particles mix. This keeps the construction stable for many years. The way asphalt is actually laid also plays an important role. Work is usually done at night when temperatures are lower. This is necessary so bitumen cools evenly and gains the required hardness. If you lay asphalt during daytime heat, its surface will cool unevenly, creating stress in the structure that will eventually lead to microcracks. After laying, roads are regularly checked using special machines equipped with sensors and thermal imaging cameras. If sections are found where temperature is too high or irregularities appear, they're repaired immediately, not waiting until the problem becomes visible to drivers. Experiments with cooling coatings deserve special mention. In some districts, asphalt is painted or covered with a special compound that reflects sunlight and reduces surface heating by 10 to 15 degrees. This is important in pedestrian areas since road surface temperature affects how hot the air gets at foot level. This way, even a regular walk becomes less exhausting. In Dubai, roads aren't left unattended until large potholes appear. Control happens constantly and systematically. Special vehicles with measuring equipment travel highways and city streets, recording the smallest irregularities. Sensors read surface deviations, and computers compare them to standards. If there's suspicion of overheating or beginning deformation, the section is checked with thermal imaging cameras. High temperature indicates that bitumen is losing rigidity, and the surface might start settling. Thanks to such monitoring, repairs are done not when it's too late, but when the first changes begin. Repair work is conducted mainly at night when temperatures are lower and material cools evenly. This extends the road's service life and avoids repeated damage. The approach is based on the idea that infrastructure should work continuously, not wait for the moment when it becomes a problem for drivers. According to Dubai municipality data, after switching to polymer-modified mixtures, the number of deformation waves on roads decreased by approximately 40% during the first 2 years. Meanwhile, road surface service life increased on average from 7 to 10 years to 12 to 15 years before the first major repair. This significantly reduces overall infrastructure costs. Although initial polymer asphalt installation costs are higher by approximately 15 to 20%, long-term savings can reach 50% due to reduced repair needs. There's also data on experimental light reflective coatings being tested in residential areas and near pedestrian zones. On average, such coatings reduce road surface temperature by 10, or even all 14 degrees, depending on conditions. According to observations, in areas with cooling roads, air temperature at pedestrian foot level also drops by 2 to 3 degrees, reducing thermal load on people and making outdoor stays more comfortable. Statistics also show that, with early detection of surface microdefects, their elimination takes on average 3 to 6 hours, while if you wait for visible damage to appear, repairs can last from several days to several weeks and require closing road sections. Therefore, the city focuses on regular monitoring. In 1 month, control vehicles can cover over 80% of the city's road network. Dubai once tested asphalt that absorbs solar energy, then radiates stored heat at night to dry roads faster after rare rainfall. Turns out, the surface works like a giant thermos. During the day, it accumulates energy, and at night gradually releases it. The experiment showed such roads can dry 30% faster. And this is really needed, because after desert rain, water doesn't absorb into the ground, but can stand on asphalt for hours or even days. So the technology solves a problem that doesn't even exist in most countries. You know how this experiment ended? Every year around the world, billions of tons of rock are blasted apart with explosives. Tunnels are carved straight through mountains, and rockets are launched into the sky. But few have ever seen the place where the force capable of reshaping landscapes in seconds is born. Today, we gained access to one of the most tightly guarded industrial facilities, where chemistry, fire, and metal come together to create the legendary TNT. The very substance whose explosive power became the world standard. But the scariest and most fascinating part isn't the explosion itself. It's how this yellow powder makes its journey from an ordinary liquid to a material that can obliterate a house-sized boulder. And trust me, if you stick around until the end, you'll learn a fact about TNT production that will completely change how you see modern industry. TNT, or trinitrotoluene as it's also called, showed up way back in the 18th century, when chemists started messing around with toluene. Americans call it TNT, short for trinitrotoluene, and to this day, it's the gold standard. 1 gram of TNT, the unit for measuring explosive force. Here at the plant, everything starts with massive tanks of toluene. This liquid flows into reactors, giant stainless steel vessels, where the temperature holds steady at 400 to 480 degrees Fahrenheit. No, seriously, it's hell in there. 200 to 250 degrees Celsius if you convert it. A mixture of nitric and sulfuric acids gets pumped inside. Concentrates so harsh, they'll melt your gloves right off. The nitration process runs anywhere from 3 hours to several days. First you get mononitrotoluene, then dinitrotoluene, and finally trinitro. The acids circulate in a closed loop. They get recycled instead of just dumping them into the ground. Operators in protective gear monitor the gauges: pressure, temperature, concentration. Everything's under control because the slightest shift and the reaction can go sideways. From the reactor, the mixture heads to coolers, long coiled tubes where the hot TNT crystallizes. Then settling tanks. The heavy TNT sinks to the bottom, while the lighter acids get drained off. That jelly-like mass right there, that's raw TNT, still wet with acid. They wash it with hot water at 150 to 180 degrees Fahrenheit to neutralize what's left. The water drains into the sewage system, and the crystals get dried in vacuum ovens, rotating drums that spin like washing machines. Massive stainless steel vats get pumped full of water at temperatures between 150 and 180 degrees Fahrenheit. The water jets out like in an industrial laundry, washing away residual nitric and sulfuric acid. TNT floats in it like jelly in boiling water, spinning, giving up impurities. The process takes half an hour. The water changes 3 times because the first batch is yellow from acid, the second is cloudy, and the third is already clear as a tear. This water doesn't just go down the drain. It gets neutralized with lime in basins, filtered through a 10-foot thick layer of sand, and then released into the river. Ecology stays under control because acid is poison for fish. Meanwhile, the crystals get unloaded. The mass becomes solid, but still 6 to 10% wet. Now comes the drying, the most interesting part. The entrance to this vacuum oven, a room where 20 rotary drums hum, each about 6 feet in diameter. TNT gets shoveled in there, 200 pounds at a time. The drum seals shut. Air pumps out until pressure drops to 100 millimeters of mercury, and heating kicks in, 130 to 140 degrees Fahrenheit. Fans blast hot air through the center. The drum spins at 30 rotations per minute, like a washing machine on spin cycle. Crystals tumble, dry evenly, don't stick to the walls. 2 hours, and the doors swing open. Pure yellow powder, temperature 40 degrees, moisture content 0.5%. A worker in a mask pours it into hoppers, where a conveyor will carry it off to granulation. 5 tons per shift from one drum, and no dust because the vacuum pulls everything into filters. The operator jokes, "Dry as my sense of humor." Without this step, TNT would clump together or detonate from moisture. An hour or two, and we've got pure yellow powder. Color? Light yellow to dark orange, depends on purity. Here we get the top grade, 98% pure product. Next up, granulation. The powder gets moistened, pressed into briquettes the size of a matchbox, then crushed down to granules 2 or 5/1000ths of an inch in diameter. Why granules? Because the powder's easier to pack, doesn't create dust, and detonates evenly. I peer into the press, a giant machine with pistons pushing 200 atmospheres of pressure, and the briquettes come out hard as rock. Then the grinders, hammer mills where the shafts spin at 6,000 revolutions per minute. Dust gets vacuumed out by ventilation, because breathing in TNT, that's gonna cost you. Now packaging. Granules pour into airtight cardboard boxes weighing 100 pounds each. That's the standard for quarries and the military. Every box gets checked for moisture. No more than 0.70%, otherwise the TNT sweats and becomes sensitive. There are also barrel forms for underwater blasts. There, the granules get mixed with paraffin so they don't get wet. Boxes are sealed, marked by lot, and done. Off to the warehouse. From here, TNT ships out to quarries, mines, defense. One box is enough to blast through 200 tons of rock. And then there's friction sensitivity. The cylinder spins for 6 hours, and if it doesn't blow, we're good. Lab techs in masks check purity with a chromatograph. Toluene or acid impurities aren't allowed. Nothing but respect. These people handle explosives like jewelers. Production is massive. 1,000 tons a month, that's millions of pounds. Energy? Electricity from gas turbines, steam from their own boilers. Waste. Acids get regenerated. Toluene gets redistilled. Environment? Filters on a 200-foot smokestack. Wastewater treated until it's clear. Neighbors don't complain. The plant sits 10 miles from the nearest town. Fun fact, TNT doesn't just explode. They melt it at 82 degrees Celsius, 250 Fahrenheit, and pour it into shells like hot wax. Or mix it with gunpowder for plastic charges. In quarries, 1 ton can shatter rock the size of a 3-story building. In mining, you can't punch through a mile-long tunnel without it. And in the military, it's the backbone of torpedoes, mines, bombs. You know how much steel came into this plant? Thousands of tons. Reactors made of chrome molybdenum steel, because regular steel just gets eaten alive by acids. I'm standing in the granulation shop right now. Hear that press rumbling? See those granules pouring into bins like golden sand? The air's clean, but it smells like nitrocellulose. Familiar scent if you've ever been to a powder plant. The operator laughs. Don't breathe too deep, or you'll detonate yourself. Joking, obviously. But the discipline? Ironclad. 8-hour shifts. Lunch break with the clatter of spoons on metal trays. Compare that to the old plants. Back then, everything by hand. Women in skirts packing TNT with bare hands. Explosions once a month. Now, robotic arms, sensors, cameras. Evolution. One worker monitors 10 processes from a control panel. And the pay? Competitive. The plant's like a living organism, roaring, churning, producing power. TNT isn't evil, it's a tool. Builds roads, digs mines, defends the country. Without it, no 1,000-foot bridges, no tunnels under mountains. Every year, humanity produces over 4 billion tons of concrete, more than any other material on the planet. It's what our cities, bridges, and roads are built from. But every crack is like a tiny timer ticking toward destruction, started the moment water seeps inside. Now imagine concrete that actually lives, breathes, and heals itself. No people, no repairs. Deep in labs across the Netherlands, USA, and Japan, a game-changing material is being born. Inside it, bacteria or microcapsules that can seal cracks on their own, just like skin healing after a wound. How is this even possible? How did a lifeless material gain the ability to regenerate? Stick around until the end, and you'll find out how scientists brought concrete to life. Self-healing concrete. Sounds like something out of a sci-fi movie, but it's already here. Scientists invented it to solve one of construction's biggest headaches, cracks. Regular concrete starts drying out and cracking over time from temperature swings, moisture, or just plain stress. And a crack isn't just a scratch. Water gets inside, the rebar starts rusting, the structure weakens, and eventually, you're looking at expensive repairs or even a collapse. That's why researchers decided to create concrete that can patch itself up, no human help required. Sounds crazy, but it's actually pretty logical. There are 2 main technologies that make this possible: microbiological and mineral. The first one uses real living organisms. So-called bioconcrete was developed by Dutch researchers, and the principle is pretty straightforward. They add special bacteria to regular concrete mix, usually Bacillus pseudofermis or Bacillus conii. These bacteria can stay dormant for years, like seeds in dry soil. Along with the bacteria, they add nutrients, usually calcium lactate. And while the concrete stays intact, the bacteria just sleep. But when a crack forms and moisture gets in, they wake up. That's when the real microscopic work begins. The bacteria start consuming the nutrient substrate and, through their life processes, produce calcium carbonate, basically the same mineral that makes up seashells and limestone. That's what seals the crack from the inside, like the concrete is fixing itself. The results are impressive. Micro cracks up to 0.03 of an inch can disappear completely within a few weeks. And all without human intervention, purely thanks to nature that's been built into an artificial material. The second technology is less alive, but no less impressive. Instead of bacteria, it uses chemistry. Tiny capsules are added to the concrete containing an active substance inside. For example, epoxy resin or sodium silicate. These grain-sized capsules are evenly distributed throughout the mix. When the concrete cracks, some of the capsules burst too. The substance inside comes out, fills the crack, and hardens on contact with air or moisture. The result is the material literally heals itself. It's similar to how certain car paints can heal scratches with heat, except this process is way more complex and large-scale. The advantage of this approach is that it works even in dry conditions, where bacteria might not activate. The downside is cost. Creating the capsules is more complex, so this concrete is pricier. But when you calculate the cost of repairing bridges or tunnels, it becomes clear. The payoff is huge. Interestingly, these technologies don't cancel each other out. Some companies are experimenting with combining biological and chemical methods to create concrete that could self-heal under any conditions. Underwater, in the desert, or in freezing cold. Testing shows that structures made with this concrete last 2 to 3 times longer than regular ones. Bridges, roads, dams, parking garages, all of this can be made nearly eternal. For example, the Netherlands already built a lakeside lifeguard station using bioconcrete, and after several years, it hasn't needed any repairs. The idea is spreading fast around the world. In the US, these materials are being tested in bridges, in the UK, in sidewalk paving, and in Japan, even in concrete for coastal reinforcements that have to withstand salt water. Regular concrete, even the highest quality, has a shelf life, roughly 50 years. After that, cracks start appearing, water penetrates inside, rebar rusts, and the structure gradually weakens. Self-healing concrete changes these rules. Thanks to bacteria or microcapsules, it can heal microdamage before it becomes a problem. That's why the service life of structures can nearly double, from 100 to 120 years. That means one bridge or building can stand for 2 human generations without major repairs. Sure, this material isn't cheap yet. It costs several times more than regular concrete, on average 3 to 5 times more. But if you look at the long game, it's totally worth it. Maintaining, repairing, and restoring structures costs governments and companies millions of dollars every year. Self-healing concrete cuts those costs to a minimum. Basically, it's like buying a car that changes its own oil and fixes its own brakes. Expensive upfront, but then smooth sailing and economical. The Netherlands became the real home of self-healing concrete. Right here, at Delft University of Technology, the idea emerged to add living bacteria to the mix that could repair concrete from the inside. The man behind this idea is Dutch microbiologist and engineer Hendrik Jonkers. Nature inspired him. He noticed that certain bacteria can survive in limestone rock and create mineral deposits, filling micro cracks in stone. That's when Jonkers asked himself, if nature can heal stone, why not make concrete that does the same? In the early 2000s, he started experiments with different bacterial strains, looking for ones that could withstand concrete's alkaline environment and stay viable for years. After numerous trials, the best candidates turned out to be Bacillus pseudofirmis and Bacillus conii, spores that can sleep for decades and activate only when moisture appears. Jonkers added them to concrete along with a food source, calcium lactate. The results were mind-blowing. When the concrete cracked, the bacteria woke up and produced calcium carbonate, which sealed the cracks like natural glue. Jonkers called his invention bioconcrete, and soon the whole world was talking about it. Later, Delft University launched a project to test bioconcrete under real-world conditions. In 2015, the Netherlands built the first lakeside structure using this material. Years later, it remained in excellent condition without any repairs. Now Jonkers' lab is working with construction companies and governments from other countries, perfecting the formula to make it cheaper and more accessible. The USA and UK bet on the mineral technology for self-healing concrete, which doesn't require living organisms, but works through special microcapsules with healing substances inside. These countries are actively investing in research on materials that can automatically restore minor damage without human involvement. The principle is pretty simple, but looks impressive. Capsules or microcapsules filled with special gel, epoxy resin, or sodium silicate are added to the concrete mix. When the concrete surface stays intact, the capsules preserve their contents without reacting with the environment. But as soon as a crack appears, the capsule ruptures and the liquid flows into the damaged zone. On contact with moisture or oxygen, the substance hardens, gluing the crack edges together and returning the structure's original strength. These systems are currently being tested in US Army labs and British research centres, including Cambridge University. In the UK, they're even building experimental road and bridge sections with this material to track how it behaves under rain, vibrations, and temperature swings. American experts went even further. They're experimenting with capsules that can activate multiple times. Inside these capsules are microgels that not only fill cracks, but also expand on contact with water, creating a hermetic barrier against corrosion. This is especially crucial for bridges and skyscrapers in coastal cities, where concrete constantly faces moisture and salts. Test results show that cracks up to a few hundredths of an inch wide can seal themselves in less than a week. And if the damage is larger, the process takes longer, but still happens without human involvement. Such technologies can significantly extend the service life of roads, tunnels, and even military structures, which is especially valuable under extreme loads. 70% of the plastic you toss in the recycling bin ends up straight in a landfill. Not because you're doing something wrong, but because traditional recycling only wants clean, single-type plastic. Everything else, dirty packaging, films, toys, shoe soles, not its problem. But there's a technology that takes any dirty, mixed plastic and turns it back into oil. No burning, no oxygen. I just visited one of only 25 facilities like this in the entire world, and I'm going to break down exactly how it works. From a pile of trash to a barrel of synthetic oil. Plus, one number from the director that makes it crystal clear. Even this is just a drop in the ocean. Regular plastic recycling, the kind you know from those triangle bins, it's super picky. It wants plastic to be one type, clean, no caps, no labels, no food residue. Plastic bottles, separate. Polyethylene, separate. Polystyrene, they often refuse to take it at all. And anything that doesn't meet these criteria, which is roughly 70% of all plastic that ends up in the trash, goes straight to the landfill, or gets burned. All that dirty food plastic, multi-layer chip bags, toys, shoe soles, films, traditional recycling doesn't want them. And that's where a different game begins. What they do at this facility is called chemical recycling, or plastic pyrolysis. And the principle is so simple, at first you don't even believe it. They take plastic and heat it without oxygen to temperatures between 550 and 900 degrees Fahrenheit. At that temperature, the long polymer chains. And plastic, if we're being brief, is just very long chemical chains, break apart into short fragments. These fragments escape as vapor, enter a condenser, cool down, and turn into liquid. This liquid is pyrolysis oil, or synthetic crude oil. The exact same product that's the starting point for making plastic, gasoline, chemicals. The circle is complete. But the gap between theory and what happens here in practice? Wide as Texas. First problem, raw materials. The plant processes anywhere from 150 to 200 tons of mixed plastic every single day. I saw this pile. It looks like where all your plastic bags, disposable lids, and thermos caps go to die. Before any of this hits the reactor, it goes through sorting, cameras, magnets, air separators. Metal has to come out completely because it just won't break down in the reactor and it clogs the equipment. Chlorinated plastics, for example, have to be separated out because when heated, they release hydrogen chloride, which literally eats the reactor from the inside. One poorly sorted container can shut down the entire line for days and cost the plant tens of thousands of dollars in repairs. After sorting, the plastic gets cut into pieces roughly 1 inch by 1 inch. This ensures even heating in the reactor. The shredders here are the size of a bus and chew through everything with a sound that makes you want to jam in earplugs and drive home. Then these pieces get fed into the reactor by an auger conveyor. The reactor, that's the key piece, and all the complexity revolves around it. It's a massive steel cylinder. This facility has 6 of them, each as tall as a 3-story building, and inside, a complete absence of oxygen is maintained. This is critical. If oxygen gets in at these temperatures, you won't get pyrolysis, you'll get ordinary combustion. Basically, a fire inside. That's why before feeding in the plastic, the system is purged with nitrogen, replacing the air with an inert gas. Oxygen sensors are mounted on every flange, and if the level rises above 0.5%, the line shuts down automatically. At 750 degrees Fahrenheit, polymer chains start breaking apart. Polyethylene, polypropylene, polystyrene, they all have different cracking temperatures, different reaction rates, different product yields. That's exactly why mixed plastic is so tricky. If you fed only pure polyethylene into the reactor, you'd get a stable 80% oil yield by weight of feedstock. With mixed plastic, that number bounces between 50 and 65% depending on batch composition. And there's no way to predict more accurately without chemical analysis of every ton. And that kind of analysis costs money. Real money. The vapor coming out of the reactor is a mixture of hydrocarbons of different sizes. It passes through a fractionation column where it separates by boiling point, almost like at a regular oil refinery. The lightest fractions are gases. They don't condense and get burned immediately in a burner to produce heat that's fed back into the reactor. At this stage, the plant is practically energy self-sufficient. It heats itself with its own gases. The middle fractions remain as pyrolysis oil, a dark, slightly viscous liquid that smells roughly like you threw a plastic bottle on a campfire and let it burn completely. The heavy fractions settle out as fuel oil or a waxy substance. And there's still a solid residue left over, carbon black or technical carbon. It gets pressed into pellets and sold to manufacturers of rubber products or pigments. There's another technical hurdle worth explaining: chlorine. Chlorine actually hides in a ton of different packaging, in dyes, additives, adhesives. When plastic with chlorine gets into the reactor, the chlorine reacts with water and forms hydrogen chloride, an extremely aggressive acid. It eats through the steel reactor walls from the inside in about 6 to 12 months instead of the projected 10 to 15 years. Replacing a single reactor costs several $1,000s and weeks of downtime for the entire production line. So chemical analysis of incoming plastic and chlorine monitoring is literally a matter of plant survival. While I was walking through the facility, one detail struck me: sensors everywhere. On every pipe, every valve, every welded joint, there are sensors for temperature, pressure, and gas composition. This entire system feeds into a central control room where 3 operators watch screens displaying roughly 300 parameters simultaneously. If pressure in any reactor jumps above the calculated value by more than 5%, an automatic valve releases the excess. If temperature drops below 2.5 degrees, cracking quality decreases and the oil comes out heavier. That's bad. If the temperature exceeds 900 degrees, gasification kicks in. Oil yield drops to zero, and all you get is gas and carbon. The window between normal and something went wrong? Literally 50 degrees. In a reactor the size of a house. The pyrolysis oil produced here gets shipped in tankers to petroleum refineries, where it's blended with regular crude and goes through cracking, turning into naphthene and xylene, which are feedstocks for making new plastic. So theoretically, a shampoo bottle could circle back to polypropylene pellets and become a new bottle. Some major chemical companies, including several from the global top 10, are already buying this oil to manufacture plastic, and even paying a premium over conventional petrochemical feedstock, because they can print "made from recycled plastic" on the packaging, and for them, that's a marketing asset. The plant director told me straight up that even if they double their capacity and hit 400 tons a day, they'll be processing less than 0.1% of the world's plastic waste stream. The solution to the problem? Either drastically cut plastic production or build several thousand of these plants across the globe. Right now, neither is anywhere on the horizon. But this plant is proof that mixed plastic pyrolysis technology can actually work at industrial scale and turn a profit, even if it's razor-thin margins with really nerve-wracking logistics. I'm walking out of here with respect for the people doing this work, and a solid sense that 92%? That number's going to stay relevant for a long time. And you know what else is going to stay relevant? Subscribing to my channel. Every year, the world melts down more than 16 million tons of silicon metal, a material without which modern civilization would simply grind to a halt. It makes steel stronger, aluminum lighter, and solar panels possible. But here's something almost nobody knows. To create just 1 ton of this metal, furnaces operate at temperatures exceeding 5,400 degrees Fahrenheit and consume as much electricity as hundreds of American households use in a month. So why does this silent giant hide a diamond structure inside? And what discovery about silicon will change your understanding of technology if you stick around till the end? Industries use metallurgical-grade silicon as a foundational material for creating ferroalloys, particularly ferrosilicon, which gets added to steel to improve its strength, corrosion resistance, and ability to withstand high temperatures. How steel deforms, its elasticity, and behavior under load largely depend on how silicon dissolved in the metal matrix behaves. Metallurgical silicon is also critical for producing aluminum alloys, where it's responsible for reducing weight and improving the alloy's ability to maintain its shape when heated. For example, in cast aluminum parts for automobiles, the silicon content can reach anywhere from 12 to 14% by weight. Another key application is obtaining purer silicon suitable for electronics and photovoltaics. Metallurgical-grade silicon serves as the starting point for producing polysilicon, which gets purified to impurity levels in the parts per billion range. This ultra-pure material is what they use to form ingots and wafers for microchips and solar panels. Demand in this sector has shot up dramatically in the US over recent decades, driven by renewable energy expansion and the needs of data centers. To put the scale in perspective, manufacturing a single solar panel module that's about 11 square feet requires roughly 6 or 7 pounds of silicon in the form of high-purity polycrystalline material. Metallurgical-grade silicon has additional applications too. It's used in chemical manufacturing to synthesize silicones, which are needed for sealants, lubricants, medical devices, household products, and electrical insulation components. It serves as the starting material for silanes, compounds that act as coupling agents between organic and inorganic materials, ensuring stronger surface bonding in composites. Certain types of silanes are used as part of adhesives and coatings that help extend the service life of structures in humid or corrosive environments. Technological progress constantly raises the bar for metallurgical-grade silicon, since purity, grain size, and consistency of properties directly impact the quality of the final product. In American industry, research continues on optimizing electric arc furnaces to cut energy consumption, as well as on utilizing carbon monoxide byproducts. On top of that, companies are developing ways to recycle silicon production waste to bring part of the material back into the cycle and reduce emissions tied to mining fresh quartz. All of this makes metallurgical-grade silicon one of the foundational industrial materials. Without it, modern electronics, transportation, and energy sectors couldn't keep up their current pace of development. To turn mineral oxide into metal, you need extremely high temperatures and a carefully controlled reduction reaction. This is done in large electric arc furnaces that operate at massive temperatures and consume enormous amounts of electricity. The furnace is loaded with crushed quartz along with carbon-based reducing agents. Most commonly, these are charcoal, coke, or various carbon briquettes, selected to ensure stable combustion and the right reactivity. Powerful graphite electrodes create an arc that heats the center of the furnace to approximately 5,430 degrees Fahrenheit. Under these conditions, ordinary rocks transform into active participants in the reaction. Silicon dioxide reacts with carbon, and as a result, oxygen is removed from the oxide. Gaseous carbon monoxide forms, while pure silicon transitions into a liquid state. The molten material is heavier than the surrounding charge, so it slowly settles to the bottom of the furnace, accumulating as a metallic mass. Once enough silicon is collected, it's released into special crucibles or troughs. As it cools down, the liquid metal solidifies into solid ingots, which are then crushed into smaller pieces that are easier to transport and process further. At this stage, it's crucial to maintain conditions that prevent impurities from oxidizing again or mixing with the cooled silicon. The raw material obtained at this point already has commercial purity of around 99%. This level of purity works fine for ferroalloys, but it's not enough for more demanding applications. Next comes the stage of refining the metal to higher purity. Silicon can be remelted in a vacuum or under an inert atmosphere, using various methods like sorption, zone melting, or chemical purification. The main goal here is to get rid of impurities like iron, aluminum, calcium, and sometimes phosphorus and boron. The impurity content is controlled with precision down to parts per million, because even a tiny amount of foreign elements can seriously affect the electrical properties of the final product. After purification, you get metallic silicon with the characteristics needed to produce alloys, silicones, or even purer polysilicon. The production process itself is energy intensive, so it's critical that the method ensures minimal heat loss and makes the most efficient use of electrical power. Modern furnaces come equipped with heat recovery systems and electrode feed control. This helps cut down overall energy consumption and boost productivity. Process optimization is a big deal here, because on average, making 1 ton of metallic silicon requires about as much electricity as several hundred American households use in a month. The quality of quartz sand plays a crucial role too. The purer the initial silicon dioxide, the fewer purification stages are needed after melting. Quartz with high impurity content can lead to increased energy consumption and greater furnace wear. That's why deposits supplying raw materials for the silicon industry must meet strict standards for chemical purity and mechanical uniformity of the material. Silicon, though it doesn't have gold's shine, is a true geochemical giant, an absolutely irreplaceable element. In terms of abundance in Earth's crust, it holds an honorable second place, losing only to a non-metal, oxygen. This means that, essentially, we live on a massive silicon-oxygen planet. It's hard to wrap your head around this, but this substance makes up a colossal 27.6% of our planetary crust's mass. Just imagine, almost every 4th ton of material we see beneath our feet is silicon or its compounds. It forms the backbone of entire mountain ranges and serves as the building material for countless minerals called silicates. This element isn't just filler. It's the foundation of our entire modern civilization. As a semiconductor, it powers every chip, processor, and transistor inside your phone, computer and car. Silicon is the gray eminence of our planet and our technological age. Quiet, abundant, but absolutely omnipotent. Its extraordinary purity is essential for microelectronics, making it one of the most demanding materials in the world. If you pick up any rock or handful of sand, you're holding an entire silicon factory. We all live on a massive silicon planet, not just a water one. Silicon could have been super expensive and sparkly, but it chose the humble path of being a semiconductor to run all the world's electronics instead. Why am I saying this? Because pure silicon has the exact same crystal structure as diamond. To put it simply, why silicon with the same structure as diamond isn't actually a diamond comes down to two key differences: atom size and bond strength. Diamond is made of carbon atoms, while silicon is made of silicon atoms. Plus, a carbon atom is tiny, whereas a silicon atom is much bigger. Even though both elements form the same spatial lattice, silicon atoms, being larger, force the whole structure to expand. This makes the bonds between them longer and, as a result, weaker. What if I told you that a high-speed train wheel experiences temperatures hot enough to make metal glow, and still can't afford to fail? Why must this piece of steel withstand tests that would destroy any car wheel in seconds? There's a reason almost nobody suspects, and if you stay with me through to the finale, you'll discover the secret process that forces the wheel to survive where other metal simply melts. But first, tell me, does your country actually manufacture railway wheels, or are they imported? A train rockets down the tracks at over 186 miles per hour. At that speed, an ordinary wheel would simply disintegrate. Why? Because it has to withstand not just weight, but a whole series of inhuman trials. The material is everything. This isn't ordinary steel used for silverware or even car bodies. High-speed train wheels are made from a special grade of steel, melted according to a unique, meticulously refined recipe. This recipe is a combination of iron with specific alloying elements, manganese, silicon, chromium, molybdenum, that give the steel extraordinary strength, toughness, the ability to absorb impacts without failing, and endurance. Beyond that, this steel must be as pure as possible, free of any foreign impurities that could become a weak point. After the special steel is melted in massive metallurgical furnaces, it's poured into molds to create large steel billets, what we call slabs or blooms. But that's just the beginning. The real transformation starts in the forging shop. This is where one of the most powerful forging presses comes into play, along with specialized forging machines. The billet, heated until it glows bright yellow or red, that's around 2000 degrees Fahrenheit, is fed under the press. The process involves multi-stage forging. It's not a single strike, but rather a whole series of controlled pressures and rotations. The giant hammers, or jaws of the press, slowly, yet with unstoppable force, flatten and shape the red-hot metal. First stage, the billet is compressed to give it a rough circular shape, densifying the metal and eliminating internal voids. Second stage, the material is flattened and rolled, forming a disc with a central hole. This is where the future wheel's outline begins to emerge, with its rim, disc, and hub. This directional metal flow shapes its internal fibrous structure, making the wheel exceptionally strong in the required directions. Forging, unlike casting, transforms steel's microstructure. It compresses the metal's grains, eliminates casting defects, and creates a directional fibrous structure that gives the wheel exceptional strength and fatigue resistance. It's like an athlete's muscles. After training, they become stronger and more resilient. Why such complexity? Because high-speed train wheels operate under extreme conditions that are hard to imagine. When moving at speeds over 186 miles per hour, the wheel's surface heats up from friction against the rails and brake pads to nearly 2000 degrees Fahrenheit. That's the temperature at which metal begins to glow red and change its properties. And this heating isn't constant, it's cyclical. Heating during acceleration and braking, cooling during movement. The material must withstand these constant temperature fluctuations without forming microcracks, which over time can lead to failure. Each pair of wheels carries a load of dozens of tons. A single railcar can weigh between 50 and 70 tons, and this weight is distributed across just 4 wheels, that is, 2 wheel sets. This creates constant pressure acting on the wheel. The train doesn't ride on a perfectly smooth surface. It crosses rail joints, uneven sections, and switches, which generate continuous impact loads. The wheel must be incredibly tough to absorb these shocks without cracking or breaking apart. After forging, the wheels aren't finished yet. They undergo complex heat treatment, which is key to developing their final properties. The wheel centers, the discs that connect the hub to the rim, are hardened. Hardening is a process of heating steel to high temperatures, then rapidly cooling it. This makes the metal harder and stronger. But hardening makes the metal brittle, so it's always followed by tempering, reheating to a lower temperature with slow cooling. Tempering reduces brittleness and improves toughness while maintaining high strength. This combination of hardening and tempering creates the ideal steel microstructure that can withstand extreme operating conditions. But even after all these complex processes, no wheel reaches the rails without brutal yet necessary testing. Every single wheel, without exception, undergoes ruthless inspections. Ultrasonic testing. It's like medical ultrasound diagnostics, but for metal. Special sensors send high-frequency ultrasonic waves through the wheel. If there's even a microscopic crack, void, or defect inside, the ultrasonic wave bounces off it and creates an echo that the instrument captures. This method allows us to see internal defects without destroying the wheels. A defect the thickness of a human hair is already grounds for rejection. Magnetic particle inspection. The wheel gets magnetized, then its surface is coated with fine ferromagnetic powder. If there's a crack, even one invisible to the naked eye, it distorts the magnetic field, and the powder concentrates along that crack, making it visible. This reveals even the tiniest surface defects that could become failure points during operation. Only wheels with perfect structure and 0 defects are cleared for installation on high-speed trains. This isn't engineering perfectionism. It's about the safety of thousands of passengers who trust their lives to these metal giants. While the United States isn't leading high-speed rail development like China or Japan, its rail network remains one of the world's largest, and American manufacturers have extensive experience producing high-quality wheels for various rolling stock, passenger trains, freight locomotives, and switching equipment alike. Unlike the automotive industry, where thousands of companies manufacture parts, the railroad wheel manufacturing market in the US is significantly more concentrated. This is a highly specialized field, requiring massive investments in metallurgical equipment, forging presses, and quality control systems. The two main and most powerful players in the North American railroad wheel manufacturing market are Amstead Rail and KF USA. While KF is a Spanish company, it maintains production facilities in the United States to meet local demand. Previously, other major manufacturers existed, but the market has consolidated. Total annual railroad wheel production in the US fluctuates, but can be estimated in the range of 300,000 to 500,000 units per year. This figure includes wheels for all types of rolling stock. It's worth noting that while the US can manufacture wheels capable of withstanding high speeds, the actual demand for wheels designed for continuous operation above 186 miles per hour remains relatively limited due to the scarce number of true high-speed rail lines in the country. For instance, Amtrak's Acela Express trains, running along the Northeast Corridor, reach speeds up to 150 miles per hour on certain segments, but not beyond the aforementioned threshold of 186 miles per hour, which requires specific material and design standards. However, US wheel manufacturing technologies and standards do enable production that meets international requirements for high-speed trains should the need arise. From a material standpoint, American manufacturers, like their global counterparts, utilize specialized grades of carbon steel alloyed with manganese, silicon, and other elements to achieve the necessary strength, wear resistance, and toughness. Forging, heat treatment, and non-destructive testing processes are standard and comply with the highest international safety and quality benchmarks. Right now, beneath our feet, millions of dollars in platinum, through which liquid stone flows at 2,000 degrees. This is a factory where sand transforms into fiber thinner than a human hair, and somehow comes out stronger than steel. Most people think the most valuable thing here is the giant furnace, but they're wrong. The most expensive part is the invisible chemistry, without which the entire material literally crumbles to dust in seconds. Every factory guards this recipe like a military secret. Without it, there'd be no modern yachts, no wind turbines, no airplane fuselages. Today, we're going where outsiders aren't allowed. And the strangest part, we're saving for the end. The whole process starts with a pile of sand and rocks. They use pure silica sand, limestone, and kaolin clay. We're talking massive volumes. Every single hour, they dump tens of thousands of pounds of this mixture into the furnace. For anyone searching for fiberglass manufacturing technology, understand this. It's not just melted glass. It's a strict chemical formula where every percentage point of borates or calcium determines whether your future boat falls apart in the middle of the ocean. These ingredients get mixed in giant hoppers and fed into the furnace, where absolute fiery chaos reigns. The temperature inside that furnace hits 2,500 degrees Fahrenheit. It's so hot that if you threw a chunk of scrap steel in there, it would vanish faster than you could blink. The glass becomes liquid like water and starts glowing with a blinding orange light. Right now, we're standing next to the main source of danger. This furnace runs non-stop for years. The furnace walls are made of special refractory brick that slowly dissolves into the molten glass. Imagine living in a house that you're slowly eating yourself. After 3 or 4 years, they have to rebuild the entire furnace, and that costs a fortune. But the real magic of this plant is hidden below. Underneath the furnace, they've installed plates called bushings. These are the most expensive pieces of hardware you'll ever see in any industry. Each plate is made from an alloy of platinum and rhodium. Why not steel? Because any other metal would simply dissolve in the hot glass or oxidize within hours. A single one of these parts can cost more than $200,000. The plant has hundreds of them. That means right beneath us, there are millions of dollars worth of precious metals with molten rock flowing through them. Each platinum plate has thousands of microscopic holes. When the liquid glass passes through them under pressure, it comes out in thin streams. And this is where the coolest stage begins, the pull. These streams don't just fall down. They're caught by a winding machine spinning at over 60 miles per hour. The glass is pulled so fast, it becomes 10 times thinner than a human hair before it even has time to cool. If you search online for how fiberglass is made, you've seen these shiny threads, but feeling their speed in real life, that's a whole different story. Here's a huge problem right at this stage. Thin glass is an incredibly brittle material. If these strands just touched each other, they'd instantly grind apart and turn into dust. So while the strand flies from the bushing to the spool, it needs to be lubricated. Every fiber gets coated with a special chemical solution. This is each factory's secret weapon. This solution protects the glass from self-destruction and lets it bond with epoxy resin later. Without this chemistry, fiberglass would just be a pile of useless glass garbage. Now we're watching thousands of strands gather into one thick yarn called roving. A single spool like this can weigh 40 pounds and hold tens of miles of continuous strand. Look at these rows of machines. They run around the clock, creating material for wind turbine blades, yacht hulls, and aircraft parts. The scale of production here is mind-blowing. In a single day, this factory churns out enough fiber to wrap around Earth's equator several times. A lot of people ask why fiberglass is so strong. The secret? Glass in fiber form has no microcracks like regular window glass does. It's pure molecular strength. Take a bundle of this fiber 1 inch thick, and you could lift a truck with it. But working with this stuff is a serious challenge. Glass dust is constantly floating in the air. Walk in here without protective gear, and within 5 minutes, your body starts itching like you fell into a patch of stinging nettles the size of a house. The workers here are used to it, but for a newcomer, it's a real test of endurance. Once the spools are wound, they're shipped to massive drying ovens. That's where the threads fully harden and the chemical protection bonds to the surface. Temperature inside those dryers? 280 degrees Fahrenheit. It's a long haul, 12 to 24 hours. If moisture gets trapped inside a spool, all bets are off. Mold, total loss of strength, you name it. For anyone interested in fiberglass construction, here's what matters. This material doesn't rot, doesn't rust. That's why shipbuilders love it. When you see enormous sheets of fiberglass cloth laid into molds for future vessels, you get why this factory matters. Without these thin threads, we'd still be building heavy, clunky structures out of metal that's terrified of every drop of salt water. The production cycle at this facility is a continuous flow of energy and materials. Every minute the furnace runs costs hundreds of dollars in gas alone. Now add the cost of maintaining platinum bushings and the salaries of specialists who know how to tame molten rock. This is an extremely high-stakes business. Any mistake in the glass formula will cause the strand to start breaking. If a break happens at 60 miles per hour, it creates a massive tangle of filaments that has to be cleaned up by hand, shutting down the entire line. Right now, we're passing the shop where fiberglass is chopped into small pieces 1 or 2 inches long. This chopped fiber is added to plastic to make it stronger. It's used to make parts for your cars, appliance housings, and even smartphones. When you're holding a tough plastic object, chances are there are thousands of tiny glass skeletons hiding inside it, made right here. At the end of our tour, we see the finished goods warehouse. Thousands of pallets stacked with gleaming white spools. They look absolutely peaceful, but inside each one lies the energy of a blazing furnace and the precision of precious metals. This production isn't just industry, it's the triumph of human ingenuity over raw matter. Turning sand into fabric that can withstand ocean pressure or open sea wind. That's what makes me marvel at these plants every single time. If you Google fiberglass applications in industry or fiberglass properties, you'll find thousands of pages of text, but nothing replaces that smell of hot glass and the feeling of static electricity coursing through your entire body on this factory floor. This is where the future of our infrastructure is born. I'm thrilled we got to peek inside this closed-off world. Fiberglass manufacturing remains one of the most secretive industries because every plant guards its own glass recipes and chemical coating formulas. It's a world of big money, extreme temperatures, and massive risks. But it's thanks to this insane process that we have lightweight cars, fast planes, and reliable buildings. I hope you enjoyed this walk through fire and platinum. We saw stone become spider silk and learned why it's so brutally difficult. Make sure to check out my other industrial deep dives where we break down the most fascinating factories on the planet. It was lively, it was scorching, and it was incredibly eye-opening. Thanks for taking this journey with me. See you on the next tour, where we'll find something else massive, complex, and absolutely one of a kind. Stay safe and keep away from molten glass unless you've got yourself a shiny silver heat suit. Worth mentioning here, a lot of people are curious about fiberglass for insulation or making composite materials, and this plant is the very first link in that entire chain. Every composite starts right here, at the platinum bushing beneath that blazing furnace. Without this foundation, there'd be no space rockets, no modern construction. See you in future videos, where we'll unlock the secrets of other off-limits facilities. Every year, billions of bolts get manufactured worldwide, so many that you could wrap them around the Earth thousands of times. But hidden in that ocean of metal, there are a select few that cost hundreds of dollars apiece, and literally have lives depending on them. Today, I'm taking you to a place where an ordinary bolt transforms into something far greater. A component that withstands extreme temperatures, crushing pressure, and even the vacuum of space. There's no factory noise here, but there is something else. Something they don't talk about openly. And if you stick around till the end, you'll understand why a $500 price tag is just the tip of the iceberg. The first thing that hits you right when you walk in? Silence. For some reason, I was expecting noise, like you'd get in a regular machine shop. But here, everything's calm. A few machines, 3 or 4 operators, and this feeling like you didn't just walk into a factory, you walked into a lab. Actually, that's exactly what it is. A lab. That also happens to be a factory. Let me walk you through how every bolt begins. The raw material is a specific nickel-chromium alloy that has to be ordered ahead of time and arrives in rods about 3/4 of an inch in diameter. One of those rods weighs around 20 pounds. It costs roughly $250, and that's before anyone's even touched it. The material isn't chosen randomly. It can withstand temperatures up to 2,000 degrees Fahrenheit, won't deform under pressure of 150,000 pounds per square inch. And here's the kicker. It doesn't lose toughness, meaning it won't go brittle like glass. A regular semi rumbles down the highway. Nothing special, no markings whatsoever. Thousands just like it roll through Connecticut every day. Inside, on wooden pallets bound with metal straps, lie the rods. Not dumped in a heap, not just thrown together, each layer separated by wooden spacers so the rods don't touch or scratch each other. Because a scratch on the raw material surface is already a detected defect that later gets damaged or cut away. One pallet, typically 40 to 60 rods, depending on length. A pallet like that weighs around 1,200 pounds. The truck can carry 6 to 8 of these pallets, meaning one trip hauls roughly $80,000 worth of material. Yet the truck itself looks no different from one hauling pens to a supermarket. At the factory, the truck backs into the loading dock, a small bay with a single door, sized specifically for one trailer. The driver backs up, the dock locks click into place, and then the forklift takes over. The operator grabs the pallet, hauls it to the raw material warehouse, a separate room with controlled temperature and humidity, because the alloy can't pick up moisture before processing. There, each pallet gets a paper tag with the batch number, delivery date, and material certificate, a document from the supplier listing the exact chemical composition of that specific melt. Without that certificate, the bars don't even make it into the plant. The driver can wait at the gate all day. And this is where things get interesting. The stuff you don't see from the outside. Before a bar hits the machine, they cut off a small chunk, about an inch long, and send it to the in-house lab for incoming inspection. They check hardness, examine the structure under a microscope, sometimes run a spectral analysis. Takes 2 to 4 hours. Only after the lab gives the green light does the batch get accepted and move into production. If the result doesn't match the certificate, they return everything, even if the difference is minimal. They cut a blank from the bar stock. A CNC machine removes material layer by layer. One blank is roughly 4 inches long. Cutting takes about 20 minutes per piece, and during that time, the machine makes approximately 2,000 individual movements with different tools. The chips that remain get collected. They're